Imagine your entire world sealed inside a metal shell, drifting between stars with no rescue, no resupply, no second chance. For centuries, every breath, every birth, every meal depends on a closed ecosystem that cannot afford to fail. So what breaks first? The machines, the biology, or the people? And how long could a generation ship really survive in deep space? Between the stars, time becomes an ocean, black, cold, and indifferent to every plan humans have ever made. In that ocean, a generation ship is not a craft so much as a wager, that a world can be carried without falling apart. This documentary follows that wager from its first clean equations to its last messy human consequences, where every subsystem becomes a promise that must be kept. We will treat the ship as 4 things at once: spacecraft, ecosystem, city, and inheritance, because it must succeed at all 4 simultaneously. The distance to even the nearest stars is not measured in miles, but in lifetimes, and every extra year multiplies the burden. What begins as propulsion math soon turns into architecture, then into medicine, agriculture, governance, and the psychology of confinement, each one quietly setting limits the engines cannot outrun. We will step inside a habitat where gravity may be manufactured, not granted, and where the simplest comfort has a structural price. Rotating rings, pressure hulls, bearings, seals, and radiators will appear not as background hardware, but as the slow-moving plot. Fatigue, creep, and microcracks writing their own calendar. Far from sunlight, energy is never just power. It is heat that must be rejected, and heat demands surface area that space can steadily erode. Meanwhile, radiation works like a patient predator, damaging DNA, flipping bits in electronics, and forcing the ship to budget protection the way it budgets food. Then comes the deeper truth. The real payload is chemistry and microbes, and the margin for error is smaller than intuition allows. Air is not there. It is continuously made, cleaned, measured, and defended against leaks that seem trivial, until centuries make them decisive. Water is not a tank, but a cycle that must survive biofilms, corrosion, trace toxins, and the quiet tyranny of consumables. Food is not a pantry, but a living factory with pests, pathogens, pollination, nutrient loops, and power demands that echo through every other system. And still, none of that answers whether the people can last. A closed population must navigate births and deaths like a control system, because too many or too few can destabilize everything. Genetics becomes arithmetic with consequences. Effective population size, drift, inbreeding, mutation load. Yet every proposed safeguard introduces new ethical weight and new failure points. Over decades, skills can fade, records can decay, and even language can drift away from the manuals that once seemed permanent. So we will ask how authority survives when scarcity is routine, when emergencies are inevitable, and when legitimacy becomes as essential as oxygen. We will examine how constitutions harden into tradition, how rationing becomes politics, and how meaning itself can function as life support, or as a spark. Beyond the hull, deep space is not empty. It is a long-duration environment of dust impacts, sandblasting atoms, and radiation storms, keeping a ledger of damage that no ceremony can cancel. Through it all, the ship must remain an industrial civilization in miniature, able to inspect, repair, fabricate, calibrate, and remember why it does what it does. By the end, we will assemble a realistic survival horizon from the interacting clocks that govern any sealed world, and we will see why endurance is rarely lost in one dramatic moment. It is lost in accumulation, in small losses, tolerated exceptions, and deferred maintenance, until the system crosses a boundary it cannot negotiate back from. The question is not whether a generation ship can be built, but whether a human world can be kept coherent as physics, biology, and human nature press on it year after year. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. Across 7 chapters, we move from interstellar distance into the ship's engineered gravity, its closed biosphere, its genetics, and its fragile social contract. And we follow the deep space hazards that quietly decide which limits are flexible and which are absolute. Space invites a simple question, and it turns brutal the moment we translate wonder into arithmetic. If we cannot outrun light, how far can a human world travel? On a clear night, The nearest star system is not a bright beacon, but a faint point hiding in the southern sky. Proxima Centauri sits about 424 light-years away, close enough to name, yet far enough to mock intuition. That distance is roughly 25 trillion miles, and it is only the first step. It is the first rung on a ladder that rises into numbers so large they stop feeling like distance. A light-year is not a place, it is a measure of time. It is the distance light crosses in 1 year, and light does that at about 186,000 miles each second. In other words, a light-year is a clock turned sideways into a ruler. We borrow the language of time because the scale is otherwise too abstract. Even our fastest spacecraft are not fast in interstellar terms. They are fast compared to airplanes, yet they crawl compared to a photon that never needs to rest. At tens of thousands of miles per hour, a probe needs millennia to reach Proxima. The number is not a dramatic exaggeration. It is the honest output of division. The fastest objects we have launched are pushed by gravity and sunlight, not by science fiction engines. Missions like Voyager and New Horizons proved what clever trajectories can do, but they also revealed the ceiling of chemical era momentum. You can propose higher speeds, and the numbers still refuse to cooperate. The problem is not imagination. It is the way energy scales when velocity climbs. Doubling speed doubles kinetic energy, and shielding demands rise with velocity. A ship that moves faster does not merely arrive sooner, it strikes harder against everything it meets. At a meaningful fraction of light speed, energy budgets become planetary. The fuel, the reactors, and the radiators stop looking like equipment and start looking like infrastructure. Propellant mass explodes, and waste heat becomes a design limit. Even if you find a perfect engine, you still have to dump heat into a vacuum that refuses to carry it away. This is where the rocket equation becomes a quiet villain. Each extra bit of speed demands more propellant, and that propellant demands more propellant to push it. The ship grows heavy, then heavier, until the mission becomes mostly fuel-pushing fuel. The math does not care how noble the goal is. Then there is impact risk, which scales with speed and never sleeps. A grain of dust becomes a bullet, and a pebble becomes a bomb. At high velocity, even a tiny particle carries the energy of a rifle round. The interstellar medium does not need to be dense to be lethal. It only needs time to deliver its hits. So the near-term reality is not a sprint. It is a long drift that outlives every crew member who launches. When speed cannot save you, endurance becomes the only strategy left. The mission stops being a trip and becomes a lineage. That is where the generation ship enters the story. It is not a ship that carries people to a destination, but a ship that becomes their home. The journey is the destination for most aboard, and that is the unsettling truth. The star ahead is a promise, but daily life is the actual landscape. Children are born under artificial skies, and elders die before any star grows large. The windows, if there are windows, show a black ocean with no shore. This premise is not romantic, it is a concession to physics. Without faster-than-light travel, time becomes the main cost of distance. It also becomes a moral cost because you are asking people to inherit a decision they did not make. What does consent mean when the ship is the only world you have ever known? Deep space sounds like emptiness, but it is a thin, hazardous ocean. The interstellar medium is sparse, yet it is everywhere, and it never stops touching you. Between stars, gas densities can drop to a few atoms per cubic centimetre. That seems like nothing, until you multiply by years and speed. Those atoms become a constant sandblasting of the hull. They are mostly hydrogen and helium, but at high speed even the simplest atom behaves like shrapnel. They also become a slow source of contamination, charge buildup and erosion. Surfaces accumulate implanted particles, coatings degrade, and exposed plastics embrittle under relentless bombardment. In a vacuum, there is no weather, yet there is still a kind of space weather. The ship's skin is always being rewritten by invisible impacts. Cosmic rays add another layer of hostility. High-energy particles from distant explosions pass through metal and tissue, leaving damage behind. Many of these particles are atomic nuclei accelerated by supernova shocks and magnetic turbulence. They arrive with energies that dwarf anything a laboratory accelerator can sustain for long. Radiation is not one event, it is a background climate. It accumulates in cells, electronics, and structural materials over decades. In biology, the danger is cumulative DNA damage and increased cancer risk, but also subtle harm to the nervous system. In machines, the danger is single event upsets, tiny bit flips that can cascade into major faults. Micrometeoroids are rarer than dust, but they are not rare enough. A pinhead impact can puncture pressure walls and shred exposed systems. The visual is deceptively calm, a smooth hull gliding through blackness with no hint of incoming debris. Yet the threat is real precisely because it offers no warning, only consequences. The silence between stars is also operational silence. Signals take years, and any help would arrive after the problem has become history. Even a simple conversation becomes an exchange of time capsules. A question sent today might be answered after the crew has changed, and after the situation that prompted it has already evolved. So the ship is not crossing a void, it is crossing a medium. It is thin, cold, and violent in ways that do not announce themselves. A generation ship must therefore be more than a vehicle. It must be simultaneously a spacecraft, a biosphere, a city, and a nation. As a spacecraft, it needs propulsion, navigation, and shielding that work for centuries. It must do this while parts age and tolerances drift, and while the original engineers are long gone. Navigation is not just pointing at a star and coasting. The ship must track its velocity, its orientation, and its long arc through the galaxy, because a small error, multiplied by time, becomes a miss. As a biosphere, it needs closed-loop air, water, and food cycles. It must keep microbes helpful, keep pathogens contained, and keep chemistry stable. On Earth, ecosystems are buffered by vast oceans and deep soils, and by a planet-sized atmosphere. On a ship, the buffer is measured in tanks, filters, and a few meters of growing medium. As a city, it needs housing, work, education, and maintenance. It must manage waste, conflict, and boredom without external relief. A city survives because people can leave, trade, or reinvent themselves in new neighborhoods. A ship removes those escape valves, and it turns every dispute into an internal pressure. As a nation, it needs governance that survives leadership turnover. It must enforce rules, adapt to crises, and preserve legitimacy across generations. History offers a warning here because even stable states fracture under scarcity and fear. What happens when scarcity is not a policy failure, but a physical boundary? The hard part is not launching a habitat. The hard part is keeping it from slowly unraveling when every subsystem depends on all others. In closed systems, failure is rarely a dramatic explosion. It is more often a gradual drift, small losses, small shortcuts, and small misunderstandings that accumulate until the world tips. Mass is the first constraint that shapes everything else. Every kilogram of shielding, soil, water, and machinery must be accelerated and protected. Water is especially telling because it is both life support and radiation shielding. The same substance that fills lungs and grows crops can also absorb particle energy, but carrying it demands enormous mass. Energy is the second constraint because nothing runs for free. Power must be reliable, repairable, and safe in a sealed environment. A ship can harvest sunlight near a star, but between stars the light is thin. That pushes the design toward long-lived power sources and towards systems that can tolerate decades of steady output without drama. Ecology is the third constraint because life is not a machine. Closed ecosystems drift, species compete, and small imbalances can cascade. A slight change in microbial communities can alter nutrient cycling, and a minor crop failure can ripple into oxygen production and morale. The system is alive, which means it is adaptive and also unpredictable. Governance is the fourth constraint because humans are not components. Incentives change, memories fade, and the mission can lose meaning. These constraints do not appear one at a time. They interact and they create failure modes that can hide for decades. A leak is not only air escaping through a crack, it is also nutrients leaving the food loop, trust leaving institutions, and attention leaving maintenance. In a sealed world, attention is a resource as real as oxygen. If maintenance becomes invisible work, it becomes easy to postpone, and postponement becomes a slow puncture. A generation ship cannot be repaired in any conventional way. It cannot dock for overhaul, and it cannot call a supply chain. It cannot evacuate to a nearby planet because there is no nearby planet. It cannot wait for rescue, because rescue would need its own generation ship. This changes the definition of risk. A minor failure on Earth becomes a compounding failure in deep space, because the margin is time. On Earth, a broken pump is an inconvenience, because a truck can deliver a replacement. On a ship, a broken pump is a question about whether the ship can still be a world. The ship must carry spare parts, tools, and raw materials. It must also carry the ability to remake parts when spares run out. That means manufacturing, metallurgy, chemistry, and computing must be embedded. The ship must be an industrial civilization in miniature. The visual here is not just a habitat ring with gardens, but workshops humming behind sealed doors. Lathes, printers, furnaces, and clean rooms become as essential as farms and clinics. Yet miniature systems are fragile because redundancy is expensive. Every backup adds mass, and every extra system adds complexity and new failure paths. Redundancy also has a human cost, because each system must be understood and maintained. A backup that no one remembers how to service is not a backup, it is dead weight. The crew must also be large enough to stay genetically and socially stable. Too few people and chance events can erase skills, diversity, and resilience. Population genetics is not a metaphor here, it is a constraint with numbers. A limited gene pool increases the risk of inherited disorders, and it reduces adaptability to disease or environmental stress. Too many people and the habitat becomes harder to feed and govern. Population is a balancing act between biology, psychology, and logistics. Time itself becomes a stressor. Materials creep, seals harden, lubricants break down, and radiation flips bits in memory. Metals fatigue under tiny vibrations, polymers outgas and crack, and adhesives lose strength in cycles of temperature and radiation. Even if nothing breaks today, the calendar keeps applying pressure. Software updates cannot assume a stable internet or a stable culture. Knowledge must be taught, archived, and defended against loss and distortion. A library is not enough if no one can interpret it. Technical literacy must be renewed each generation, because the ship's survival depends on competence, not just tradition. Even language can drift, and drift can break procedures. A maintenance manual that becomes unreadable is another kind of hull breach. The mission story must also survive. If the destination is centuries away, why obey rationing, why accept risk, and why keep working? Some answers are ethical, some are coercive, and some are cultural. None are guaranteed to hold across births, deaths, and power shifts. Human history is filled with long projects that outlasted their founders, from cathedrals to canals. Those projects were built on Earth, with fresh workers arriving and with failure cushioned by a larger world. A generation ship removes that cushion, and it makes continuity a life support system. The story is not decoration, it is structural, because it binds strangers into a single plan. So the central question is not whether humans can endure hardship. The question is whether a closed world can remain coherent long enough to arrive. This documentary treats the ship as an experiment with no reset button. We will ask what breaks first, and what failure looks like in slow motion. We will examine the earliest cracks in the system, because early cracks teach you where the stress is hiding. We will look at air and water loops, food production, radiation exposure, and material fatigue. We will look at governance and mental health, because social collapse is also a technical failure. A ship that cannot coordinate cannot maintain itself, and a ship that cannot maintain itself cannot stay sealed. We will look at population dynamics, because survival is statistical. A few bad years can reshape the gene pool, the labour pool, and the future. We will look at energy sources, because power is the heartbeat. If the lights flicker, everything else becomes triage, and triage becomes a way of life. We will look at navigation and collision risk, because the medium is not empty. A single untracked object can end centuries of planning in seconds. We will also look at the paradox of safety. The more tightly you seal a world, the more you trap heat, toxins, and mistakes. The stakes are not only technical, they are existential. A generation ship is a bet that humanity can carry its own Earth in a metal shell. If it succeeds, it proves that distance is not a prison. If it fails, it shows that the universe punishes closed systems without mercy. Interstellar space does not care about our intentions. It does not reward courage, and it does not forgive small errors repeated for years. The distance to the nearest star is already longer than a career, a marriage, or a lifetime. For a generation ship, it is longer than memory, and longer than the living chain of first-hand witnesses. So we begin with a reality check that feels like a riddle. How do you build a world that cannot leak life when every system must breathe? From here, the story turns from astronomy to engineering. The next step is to define the vessel that could even attempt the crossing. We move from cosmic distance to the first practical question. What kind of ship can stay sealed, stable, and sane for centuries in deep space? From here, the story turns from astronomy to engineering. The distance problem becomes a habitat problem, because the ship must be livable for centuries. In a telescope, a few light years look like a gap in a star field. In a hull, that same gap becomes years of air, water, food, and repair. A generation ship is not one machine. It is a stack of compromises that must hold together across time, wear, and human turnover. Every subsystem is a promise made to people who are not yet born. The ship must keep that promise while materials age, skills drift, and priorities change. The hull is the first boundary. It separates a thin bubble of pressure, water, and warmth from a vacuum that offers no forgiveness. Visually, it is a quiet curve of metal and composite, smooth, almost serene. Yet on the outside, micrometeoroids arrive like invisible bullets, and on the inside, every seam becomes a potential leak path. Inside that boundary, the ship must provide gravity, protection, power, and repair. Each choice changes mass, complexity, and the odds of long survival. The design is never finished, because the ship is a moving city with a finite warehouse. Even a small improvement in one area can demand a large sacrifice in another. Gravity is not a luxury on a century timeline. Without it, bones thin, muscles waste, fluids shift, and pregnancy becomes a medical unknown. We understand the short-term physiology from orbital stations, where calcium loss and cardiovascular deconditioning appear within months. What we do not understand is the multi-decade version, how development, childhood growth, and aging behave without a constant downward pull. We can medicate and exercise for months in microgravity. We do not know if those countermeasures can carry a civilization for generations. Exercise devices also require maintenance, bearings, seals, and spare parts, which means they are not just medical hardware. They become part of the ship's industrial burden, and that burden compounds with time, so designers reach for artificial gravity. Two families of solutions dominate the conversation: rotation habitats and constant acceleration flight. Both are attempts to trick biology into thinking it still lives on a planet. Both also reveal how stubborn physics becomes when you stretch a mission across centuries. Constant acceleration sounds like the cleanest answer. If you accelerate at 1 g for half the trip, you get gravity and high speed. The ship becomes a torch, always pushing, always falling forward. In the mind's eye, it is elegant, an arrow of light and thrust turning deep space into a corridor. Then you flip and decelerate for the second half, in a short story that turns interstellar travel into a human-scale commute. The stars stop being distant destinations and become places you can arrive at, with schedules and arrival windows. It is a seductive narrative, because it replaces waiting with motion. In physics, it turns into a fuel and energy cliff. Continuous acceleration demands propellant and power on a scale that dwarfs the habitat. The kinetic energy alone grows with the square of velocity, and the required momentum change never stops. You're not paying once for speed, you are paying continuously for time. Even a gentle fraction of 1 g, sustained for years, implies exhaust velocities and mass ratios that approach the absurd. The rocket equation does not negotiate. It is a logarithm that punishes optimism, because every extra meter per second demands exponential propellant growth. When the timeline is measured in decades, the arithmetic becomes merciless. If the ship carries reaction mass, it becomes mostly propellant. Tanks dominate the silhouette, and the living volume becomes a small island in a sea of stored momentum. If it does not carry reaction mass, it needs an external medium or a beam which becomes its own infrastructure. That infrastructure must be built, aimed, powered, and maintained, often from home, across interstellar distances. So for near-term concepts, constant acceleration is a sprint fantasy. A generation ship is more likely to boost, coast for decades, then break. The engines roar early, then fall silent, and the ship becomes a drifting habitat with a long memory. The mission's drama shifts from thrust to endurance. That makes rotation the practical gravity option. You build a world that spins, and you let centripetal acceleration imitate weight. The trick is simple in principle. A curved floor pushes up on your feet. The complexity arrives when you ask that trick to work every day, for every person, across centuries. The idea is older than spaceflight. Engineers sketched rotating wheels and cylinders as soon as they understood that vacuum does not provide down. In the early 20th century, long before rockets reached orbit, writers and physicists imagined spinning stations as the obvious answer. Those drawings were not naive, They were early acknowledgements that human bodies are tuned to gravity. In the modern imagination, two reference designs appear again and again. The Stanford torus is a ring with spokes and a hub. It reads like a bicycle wheel turned into a neighbourhood, with windows looking inward and outward. The O'Neill cylinder is a long rotating drum, big enough to hold landscapes and weather-like systems. Both trade propulsion complexity for structural complexity, and both demand materials that behave predictably under constant tension. Rotation creates gravity that depends on radius and spin rate. Small radii require fast rotation, and fast rotation creates disorienting Coriolis forces. The basic relationship is simple. Acceleration equals omega squared times radius. But the human experience of that acceleration is not simple, because the inner ear is not a physics equation. Coriolis effects are not abstract. They change how water pours, how people walk, and how the inner ear interprets motion. In a rotating habitat, a tossed ball curves, and a falling object lands slightly sideways. Even the air can develop subtle circulation patterns because moving fluids feel apparent forces. At high spin rates, simple movements can feel like sideways pushes. That can mean chronic nausea, reduced performance, and a constant tax on daily life. Turn your head quickly and your vestibular system receives conflicting signals. Over time, people may adapt, but adaptation is not guaranteed, and it may vary across ages and individuals. So designers want large radii. A larger ring can spin slower to reach 1G, and slower spin reduces Coriolis stress on the body. It also makes the horizon feel less curved, which matters psychologically. A world that looks like a world is easier to live in, even when you know it is steel. Large radii also raise structural demands. The habitat wants to fly apart, and the tension in the ring becomes a permanent load. In a torus or cylinder, the structure is always in hoop stress, always being pulled outward by its own rotation. That stress does not rest, and it does not forgive small flaws. Materials must handle that load for centuries, across thermal cycling and radiation damage. Fatigue and microcracks become long-term enemies. Metals can creep under constant stress, and composites can delaminate if their interfaces degrade. The ship must be built like a bridge that never stops vibrating, because rotation is a continuous mechanical insistence. The rotating structure also complicates docking, maintenance, and internal logistics. You need bearings, seals, or separate non-rotating sections for engines and radiators. Visually, this becomes a choreography of frames, one part spinning, another holding still, with interfaces that must remain aligned. Every interface is a place where wear can accumulate quietly. Bearings that run for centuries are not a trivial component. Any friction becomes heat, wear becomes debris, and misalignment becomes vibration. Lubricants can break down, and surfaces can pit, especially under radiation and vacuum conditions. A bearing failure is not dramatic like an explosion. It is a slow loss of smoothness, then a cascade of stresses. Some designs avoid large bearings by spinning the whole ship. That simplifies interfaces, but it forces every external system to live on a rotating frame. Radiators, antennas, and engine mounts must all tolerate rotation, which changes how they deploy and how they point. The ship becomes a single spinning instrument, and every subsystem must accept that rhythm. Other designs keep a stationary spine and spin only the habitat. That creates a clear engineering boundary, and it also creates a single point of failure. The spine becomes the place for engines, navigation, and heat rejection, while the ring becomes the place for life. The boundary between them must be reliable enough to survive not only physics, but also institutional neglect. Either way, artificial gravity is not one decision. It is a web of decisions about radius, RPM, structural margin, and human tolerance. The ship's designers must decide what good enough means, and then defend that definition for generations. Even the cultural habits of the crew, how they move, how they build, how they exercise, become part of the gravity system. Gravity is only one part of tolerable life. The next invisible constraint is radiation, which does not announce itself until damage has accumulated. You cannot smell it, and you cannot feel it, until the consequences arrive later. In that sense, radiation is the ship's most patient predator. In deep space, the ship is exposed to galactic cosmic rays. These are high-energy nuclei accelerated by distant astrophysical violence. Many are protons, but a significant fraction are heavier ions, stripped of electrons and moving at relativistic speeds. When they hit tissue, they deposit energy along dense tracks, damaging DNA in complex ways. They arrive constantly, and they are hard to stop. They punch through metal, electronics, and tissue, leaving ionization tracks behind. A cosmic ray can pass through a wall and still carry enough energy to matter on the other side. Over years, that steady drizzle becomes a climate of risk. The ship is also threatened by solar particle events. A star can throw bursts of energetic protons that spike dose rates in hours. The Sun is not unique in this behavior, and a ship traveling between stars cannot assume a gentle stellar environment. The crew must treat space weather as a real operational variable, not a rare headline. Cosmic rays are the background climate. Solar storms are the sudden weather, and both can shape a mission's medical and operational limits. A storm can force everyone into a shelter, like passengers moving below deck in a hurricane. The difference is that the storm is made of particles, and the shelter is made of mass. Radiation is not only a biological problem, it flips bits in memory, degrades sensors, and causes single-event upsets that can cascade into system faults. A high-energy ion can deposit charge in a transistor and change a stored value, turning a 1 into a 0. Over long missions, electronics must be treated like living things, monitored, corrected, and periodically renewed. Shielding seems like a straightforward answer. You put mass between people and particles, and you accept the weight penalty. In a diagram, it looks easy. Thicker walls, safer crew. In practice, shielding is a negotiation with particle physics, because not all mass behaves the same, but shielding has a cruel detail. High-energy particles can strike shielding and create secondary radiation, including neutrons and lighter fragments. The original particle may be stopped, yet its collision can produce a spray that penetrates deeper. The result can be a more complicated radiation field inside the habitat, not a simple reduction. More shielding can sometimes create more complex radiation fields. The goal becomes dose reduction, not a simple wall of metal. Designers must model how particles fragment, scatter, and slow, which means the ship's walls become a carefully engineered radiation environment. The hull is not just structure, it is a medical device. Hydrogen-rich materials are often favoured because they slow charged particles efficiently and reduce secondary production. Water, polyethylene, and other plastics become dual-use assets. Hydrogen nuclei are similar in mass to incoming protons, so they can absorb energy without producing as many damaging fragments. In plain terms, light atoms can be kinder shields than heavy ones. Water is especially valuable. It is life support, thermal mass, and shielding, and it can be placed where people spend the most time. Visually, imagine translucent tanks lining corridors, glowing faintly under maintenance lights. The ship's most precious substance becomes a wall, and the wall becomes part of the ship's survival logic. Designers imagine water tanks wrapped around sleeping quarters. They imagine storm shelters with extra shielding for solar events. A shelter might be a compact room near the center of mass surrounded by water, food stores, and equipment. During an alert, the ship's daily life compresses into that protected volume, and time becomes measured in dose rates. Ice can serve the same role, and it stores well. Regolith, if carried from a launch site or mined later, offers bulk shielding at high mass cost. Ice is stable and dense, and it can be integrated into thermal systems as a buffer. Regolith is blunt and heavy, effective but expensive to move, and difficult to integrate without structural penalties. Every kilogram of shielding must be accelerated, steered, and protected. The ship's mass budget becomes a moral argument about safety versus feasibility. Add more shielding, and you reduce cancer risk, but you increase propulsion demands and structural stress. The ship's designers are forced to quantify harm in two currencies at once. Magnetic shielding is the tempting alternative. If you can bend charged particles with fields, you might replace mass with power and superconductors. The image is dramatic. Invisible lines of force wrapping the ship like an aurora. It echoes Earth's magnetosphere, which deflects many solar particles before they reach the surface. The concept has limits. Galactic cosmic rays are extremely energetic, and the fields required can be enormous and difficult to sustain. Strong fields demand large coils, stable cryogenics, and careful management of stored magnetic energy. A quench event, where a superconductor suddenly becomes resistive, can release heat and stress in seconds. Magnetic shielding also does little against neutral secondaries. It introduces new failure modes, including quench events and strong field hazards inside the habitat. Fields can interfere with instruments, induce currents in structures, and complicate medical equipment. Even if it works, it becomes another system that must be maintained for centuries. So most credible designs return to passive shielding. They accept that the ship must be heavy, because biology is fragile and time is long. The hull thickens, the internal layout becomes layered, and the most protected spaces move toward the centre. The ship begins to resemble a geological cross-section, with safe strata and exposed strata. Mass then collides with another constraint. A sealed habitat is a heat engine, and every watt of waste heat must leave through radiation. In a closed world, energy does not disappear. It changes form and ends as heat. The ship can be perfectly efficient in theory, yet it still must glow in infrared to survive. In vacuum, there is no air to carry heat away. Conduction and convection end at the hull, and the only exit is infrared photons. That is a strange fact to live with, because it makes heat rejection feel like a kind of slow light. The ship must shine its waste into darkness, constantly, without pause. That makes radiators as essential as reactors. Power generation, life support, computing, lighting, and industry all become heat that must be rejected. Even human bodies are heat sources, and a large population becomes a measurable thermal load. The ship's energy budget therefore becomes a thermal budget, whether the crew thinks about it or not. Radiator area scales with power and with temperature. If you want compact radiators, you run them hotter, which stresses materials and increases risk. Hotter radiators also glow brighter in infrared, which may matter for detection, though stealth is rarely the primary concern. Cooler radiators are gentler, but they demand enormous surface area. If you run them cooler, you need more area, which increases mass, deployment complexity, and exposure to micrometeoroids. A radiator farm can stretch like wings, thin panels stitched with coolant lines. It is visually delicate, like a leaf skeleton, yet it carries the burden of the ship's survival. In deep space, fragility is not an aesthetic, it is a hazard. This is the radiator paradox. The ship needs large, delicate surfaces to survive thermodynamically, in an environment that punishes delicate surfaces. There is no perfect answer, only strategies to fail slowly. The ship must assume damage will happen, then design so that damage is not destiny. Micrometeoroids and dust do not need to be common. Over centuries, rare events become expected events. A grain of sand at interstellar relative speeds carries enormous kinetic energy, and even smaller particles can erode surfaces over time. The ship's radiators live in that slow storm year after year. A single puncture does not have to be fatal, but it must be anticipated. Radiators need segmentation, isolation valves, and bypass loops. Coolant circuits must be able to reroute around damage, and leaks must be detectable before they drain a system. The ship's thermal control becomes a network designed for surgical isolation. They need graceful degradation, or a damaged panel reduces capacity but does not cascade into total thermal failure. Heat management becomes a reliability discipline. The crew must understand thermal margins the way sailors understand ballast and weather. When margins shrink, the ship's lifestyle may have to change. Less industry, fewer lights, reduced power peaks. Thermal design also shapes layout. Hot industrial zones, reactors, and power electronics want separation from farms and living spaces. Heat pipes, coolant loops, and radiative pathways become the ship's hidden geography. In Cutaway, you would see a city built around plumbing, with corridors that exist because pipes must pass. The ship becomes a thermodynamic map. It is organized around heat sources, heat sinks, and the plumbing that connects them. Even the rotation habitat influences this map because spinning structures complicate fluid routing and maintenance access. The ship's internal architecture is therefore a compromise between comfort and serviceability. Once you accept that nothing can be resupplied, reliability becomes the central architecture. The ship must be designed to be repaired by its own descendants. That requirement changes the meaning of finished, because the ship is never truly complete. It is a project handed from one generation to the next, with manuals that must remain legible. Redundancy is the first tool. You duplicate critical systems, and you accept the mass penalty as the price of survival. A second air scrubber is not wasteful when the nearest spare parts store is a star system away. Yet duplication also means more valves, more sensors, more failure points, and more training. But redundancy is not free safety. Every extra system adds complexity, and complexity creates new ways to fail and new skills to maintain. A backup that is never tested becomes a myth, and a backup that is tested too often wears out. The ship must develop a culture of verification, because faith is not an engineering method, so designers prioritize. Some subsystems get full duplication, others get partial backups, and some rely on repair rather than replacement. The decision depends on failure consequences and repair difficulty. A failed pump might be fixable, while a failed pressure bulkhead is existential. The architecture becomes a hierarchy of what must not fail. Maintainability becomes a design requirement, not an afterthought. Components must be accessible, modular and removable without dismantling the ship. Access panels are not cosmetic and crawl spaces are not luxury. They are the difference between a repair and a slow surrender. A pump that cannot be reached is not a pump. It is a timed failure waiting for the first generation that lacks the tools to reach it. Over centuries, even knowledge can become inaccessible, not because it is lost, but because it is buried in obsolete formats. The ship must treat documentation like a life support resource. Modularity also supports isolation. When a subsystem becomes contaminated or damaged, it can be sealed off while the rest of the ship keeps running. Isolation is how a closed world prevents local problems from becoming global ones. In visual terms, bulkhead doors and valve trees become the ship's immune system. Over centuries, cannibalization becomes a strategy. Old modules become parts donors, and the ship's history becomes a warehouse of salvage. A retired workshop might be left intact, not for nostalgia, but because its fittings may be needed later. The ship carries its own ruins, and those ruins are valuable. That only works if interfaces are standardized. A civilization ship needs design rules that persist, even as technology evolves inside the hull. Standard bolt patterns, connector types, and pressure ratings become cultural artifacts. The ship must resist the temptation to customize everything, because customization is expensive when you cannot replace it. Spare parts eventually run out. At that point, the ship must manufacture what it needs, from raw stock to finished components. This is the moment when a habitat becomes an economy. The ship stops being a consumer of inventory and becomes a producer of capability. Onboard manufacturing is not a convenience. It is a survival multiplier, because it turns mass into capability rather than into a fixed inventory. A block of alloy is potential, while a specific spare part is a single answer to a single question. Manufacturing keeps options open, and options are what time consumes. Machine tools matter as much as 3D printers. Additive manufacturing can produce shapes, but precision surfaces and strong alloys still demand machining and heat treatment. Bearings, seals, and mating surfaces often require tolerances that printers struggle to achieve reliably. The ship therefore needs lathes, mills, grinders, and metrology equipment that can be calibrated over decades. Metallurgy becomes a life support skill. The ship needs furnaces, casting capability, and controlled atmospheres for welding and sintering. Heat treatment schedules must be known and repeatable, because strength depends on microstructure, not just composition. In a closed habitat, even fumes and particulates from industry must be managed, because the air is shared. Polymers and composites also matter. Seals, insulation, and flexible parts degrade, and the ship must be able to remake them. Plastics can embrittle under radiation, and elastomers can harden with time and exposure. A cracked gasket is a small failure, yet in a closed world it can become a persistent leak, and leaks are cumulative. Electronics are harder. Chips require clean rooms and complex supply chains, so designs may favor radiation-hardened simplicity and repairable architectures. Instead of chasing maximum performance, the ship may choose longevity, modular boards, and conservative voltages. The goal is not speed. The goal is predictability. Computing must be robust to bit flips and aging storage. Error correction, redundancy, and periodic verification become routine maintenance, like cleaning filters. Software must also be maintainable, because a system that cannot be updated becomes a fossil. Over time, the ship's computational infrastructure becomes a library that must be curated. The ship becomes an industrial ecology. Waste streams become feedstocks, broken parts become raw material, and manufacturing becomes part of the daily economy. Nothing is truly thrown away because away does not exist. The ship's trash is simply matter waiting to be reclassified. All of this depends on energy. Power is the heartbeat, and the propulsion system is the largest single claim on that heartbeat. Even when engines are off, life support, lighting, agriculture, and industry require steady power. The ship must therefore plan for peak loads, maintenance outages, and the slow decline of components. Near-term propulsion options are constrained by what we can plausibly build and maintain. Chemical rockets can launch, but they cannot push a world between stars. Their exhaust velocity is too low, which means propellant demands explode for interstellar delta V. Chemical is a ladder to orbit, not a bridge to another sun. Nuclear thermal propulsion offers high thrust and better efficiency than chemical. It could shorten the initial boost phase, but it still demands large propellant stores. A reactor heats propellant directly, which is efficient, but the propellant still must be carried. Over a generation ship scale, even better can remain insufficient. Nuclear electric propulsion trades thrust for efficiency. It can run for long periods, but it requires reactors, power conversion, and large radiators. Ion or plasma thrusters sip propellant, yet they demand electrical power, and power becomes heat. The ship's propulsion choice therefore echoes through its thermal design. Fusion is the aspirational case. It promises high exhaust velocity and reduced propellant mass, but it demands confinement, materials, and reliability beyond current practice. A fusion engine must handle intense neutron fluxes, erosion, and complex control systems. The dream is powerful, yet the question is not only whether it can work, but whether it can keep working. Even with advanced propulsion, a generation ship likely spends most of its life coasting. Engines burn early, then the ship becomes a drifting habitat. Visually, the plume fades, and the ship's bright mechanical drama disappears. What remains is a rotating world, quietly carrying its people through a black ocean. Coasting is not passive. Systems still age, the trajectory still evolves, and small errors still accumulate into large misses. A slow leak of propellant, a tiny asymmetry in thrust, or a subtle gravitational nudge can shift the path. Over decades, the ship's course becomes a thing that must be watched like a patient's vital signs. Course correction over centuries requires navigation that does not depend on Earth. The ship must know where it is, where it's pointing, and how it is drifting. Earth will become a dim star behind it, and radio signals will take years to arrive. Autonomy is not a feature. It is the only possible mode. Star tracking provides orientation. It compares known star fields to measured angles, and it can detect slow rotation errors and pointing drift. Cameras and optical sensors become the ship's eyes, and star catalogues become its memory. This is ancient navigation, updated for a new ocean. Inertial measurement provides continuity between observations. Over long times, sensors drift, so calibration becomes a ritual, not a one-time procedure. Gyroscopes and accelerometers accumulate bias, and bias becomes error. The ship must therefore schedule regular checks, and those checks must survive changes in leadership and culture. Pulsar timing is a deeper option. Millisecond pulsars act like cosmic lighthouses, and their regular pulses can support position fixes far from the sun. The pulses are so stable that they resemble natural atomic clocks, though they are faint and difficult to detect. In visual terms, it is navigation by listening to the galaxy's metronomes. Pulsar navigation has limits. Signals are weak, detectors must be stable, and timing systems must remain accurate across decades of component replacement. The ship must preserve not only hardware, but also calibration knowledge. A timing system that drifts unnoticed can turn a precise method into a confident mistake. The ship also needs a map of its own motion. Interstellar space is not empty, and gravitational tides and passing stars can perturb a long trajectory. Even the distribution of interstellar gas and dust can matter for long-term planning, if it affects erosion and shielding. The ship is moving through an environment, not through nothing. Even tiny velocity errors matter. Over 100 years, a millimeter per second becomes thousands of kilometers of missed distance. That is the quiet terror of long baselines. A small neglect today becomes a large correction tomorrow, and corrections cost propellant and power. So navigation is a maintenance problem. It requires sensors, computation, and the institutional habit of checking the ship's path. The habit is as important as the hardware, because hardware can be replaced, while habits must be taught. The ship must make navigation part of its identity, like a tradition that keeps it honest. Propulsion for corrections can be modest. Small thrusters, ion engines, or mass drivers can trim the trajectory if propellant and power are budgeted. The corrections might be tiny, but they must be reliable, and they must be available late in the mission. A ship that cannot steer becomes a drifting monument. That returns us to the brutal arithmetic. Every design choice competes for mass, volume, and energy, and each competition shapes the ship's social reality. Engineering decisions become lifestyle decisions, because the ship's inhabitants live inside the consequences. A heavier ship might be safer from radiation, yet it might require a smaller habitat to stay launchable. If you add shielding, you add mass. If you add mass, you need more propulsion, more structure, and more radiators to handle more power. Each layer of safety demands another layer of support. The ship becomes an onion of dependencies, and the core remains human. If you add redundancy, you add complexity. If you add complexity, you need more training, more documentation, and more time spent maintaining instead of living. A society that spends too much time fixing its world may forget how to enjoy it. Yet a society that stops fixing its world will not keep it. If you shrink the habitat to save mass, you raise crowding and stress. If you expand it for comfort, you increase everything that must be protected. Space is not only volume, it is psychological bandwidth. How much privacy can a closed world afford, and what happens when it cannot? The ship is therefore an engineered ecosystem container moving through a cosmological environment. Its architecture is a negotiation between physics and tolerance. It must be strong enough to resist vacuum, smart enough to manage heat, and humble enough to accept that humans are not infinitely adaptable. The ship is a machine, but it is also a home, and those two roles sometimes disagree. The mystery is that the ship can look stable while it slowly drifts toward failure. A seal hardens, a bearing wears, a radiation dose accumulates, and the calendar keeps moving. The lights still turn on, the air still tastes normal, and the floors still feel like floors. That is what makes long missions dangerous. Failure can be quiet. The ship's designers can buy time with margins. They can buy time with modularity, with repair culture, and with the ability to remake what breaks. They can also buy time with conservative choices, choosing lower stresses and lower temperatures even when it costs mass. But every purchase comes from the same finite budget, and the budget is carried as inertia. But time is the one resource that cannot be stored. A generation ship survives by turning time into routine, and routine into resilience. Maintenance schedules become calendars, and calendars become culture. The ship's true technology may be its ability to keep doing the boring things correctly forever. The hull can be strong, and the engines can be clever. But the true payload is biology, and biology sets the most unforgiving requirements. A human body is not a rugged machine, and a human society is not a stable algorithm. The ship must protect both, even when they change. Next, we move from architecture to ecology. Can you keep an ecosystem stable when every molecule must be accounted for? When a closed world exhales, where does the carbon go? And how do you guarantee it comes back as food? In a generation ship, survival is not only built, it is balanced. The hull can be strong, and the engines can be clever, yet the true payload is biology. In deep space, the ship is not mainly a vehicle problem, it is a biosphere problem, where every atom must keep circulating. A closed world is defined by mass balance, which is a simple rule with merciless consequences. If oxygen leaves the air, it must appear somewhere else, or people suffocate. If carbon dioxide rises, it is not just discomfort. It becomes chemistry, crop yield, cognition, and long-term survival. On Earth, the atmosphere is a vast buffer that forgives mistakes, because winds and oceans dilute what we emit. On a ship, the buffer is measured in cubic meters and response time. The air is not a background, it is a constantly engineered chemical system. Visually, imagine a habitat corridor where nothing looks unusual, yet the air itself is a managed fluid. Fans whisper behind panels and ducts pulse with steady circulation. Every breath is a transaction, and every transaction must be recorded. In a sealed volume, even a small bookkeeping error becomes a slow catastrophe. Start with oxygen and carbon, because they define the daily rhythm of living tissue. Humans consume oxygen and exhale carbon dioxide, and microbes do the same. Plants reverse that flow in light, yet they also respire in darkness. The ship must manage day and night as a metabolic schedule. Photosynthesis is not only plants making oxygen, because it is a chemical conversion with limits. Chloroplasts use photons to split water and move electrons, building sugars from carbon dioxide. That chemistry has a ceiling set by light intensity, temperature, and nutrient availability. When any one factor slips, the oxygen ledger slips with it. In a sealed habitat, oxygen is not produced by magic. It is produced by photosynthesis, electrolysis, or stored chemical reserves, each with costs. Every option ties life support to power, maintenance, and failure modes. Electrolysis, for example, is straightforward in principle and demanding in practice. You push current through water, generating oxygen and hydrogen, and you must keep membranes clean and catalysts active. The oxygen is life, but the hydrogen is also risk. It is fuel, reagent, and explosive hazard, often all at once. Stored oxygen buys time, not independence, because tanks are finite mass. Chemical oxygen candles and chlorate systems can provide emergency supply. They also generate heat and byproducts that must be managed. In a ship designed for centuries, emergency becomes a recurring category. The International Space Station offers a partial lesson and also a trap. ISS life support recycles water and scrubs carbon dioxide, yet it relies on resupply. Filters, sorbents, and spare parts arrive on cargo ships, and closure is never fully tested. ISS also teaches a subtler point about operations. Astronauts spend time maintaining the machines that keep them alive. They replace canisters, clean separators, and track sensor readings like vital signs. A generation ship inherits that reality, but it cannot inherit the supply chain. A generation ship cannot treat resupply as a hidden subsystem. True closure means the ship must regenerate consumables indefinitely. It must also track losses that are tiny per day, yet fatal over decades. This is where the narration becomes almost geological in scale. A few grams of oxygen lost each day feels trivial. Over 100 years, it becomes a missing atmosphere. The ship must think like a planet, but with a volume smaller than a stadium. Carbon dioxide control is the first constant battle, because CO2 rises quickly and affects humans early. You can scrub CO2 with chemical sorbents, then vent it, but venting is mass loss. You can capture CO2 and reduce it, but reduction needs hydrogen and catalysts. You can feed it to plants and algae, but that requires stable agriculture. On ISS, CO2 scrubbing has often relied on solid amine beds or lithium hydroxide canisters. Those systems work, but they saturate, and saturation is a countdown. Regenerable sorbents must be heated or vacuumed to release CO2. That released CO2 then becomes either waste or feedstock for the next loop. Reduction closes the carbon loop more tightly, but it is chemically picky. The Sabatier reaction can combine CO2 with hydrogen to produce methane and water. The water can be electrolyzed again, returning oxygen to the air. Yet methane is then a decision: store it, burn it, or vent it and accept loss. Even when CO2 is controlled, oxygen can drift in ways that are hard to notice. Leaks, corrosion, and side reactions consume oxygen without producing food. Fires are rare, yet even small combustion events can shift inventories. The ship must treat oxygen as both life support and oxidizer. A tiny leak is not only a pressure problem, because it is a composition problem. Oxygen can be preferentially consumed by oxidation of metals and polymers. That means the remaining air can drift toward higher nitrogen fraction. People may feel fine until the margin is gone. Nitrogen is the quieter constraint, because it shapes both air pressure and food. Humans need nitrogen in proteins, and plants need it in usable forms. The atmosphere can hold nitrogen, yet crops cannot eat N2 directly. The ship must run a nitrogen economy. That economy is a chain of transformations, and each link can fail silently. Plants mostly use nitrate and ammonium, not nitrogen gas. On Earth, microbes in soils and roots do the conversion for free, powered by sunlight and ecology. In a ship, for free becomes for engineered stability. On Earth, nitrogen cycling is powered by soils, lightning, and vast microbial communities. In a ship, nitrogen fixation must be engineered or biologically maintained. If nitrate production falters, yields drop, and the air may still look normal. The crisis arrives as hunger first, then as cascading system stress. Nitrogen fixation is energetically expensive because the NN bond is stubborn. Industrially, the Haber-Bosch process breaks it using high pressure, high temperature and catalysts. That history matters because it reshaped Earth's agriculture in the 20th century. A ship must decide whether it can afford that kind of industrial intensity in miniature. Biological fixation is gentler, but it is also fragile. Certain bacteria and archaea use nitrogenase enzymes to convert N2 into ammonia. Those enzymes are sensitive to oxygen, which creates a paradox inside an oxygenated habitat. The ship must provide protected niches where fixation can occur without poisoning itself. Ammonia is both nutrient and toxin. It can accumulate from waste processing, leaks, and decomposition, and it irritates lungs at low levels. The ship must keep ammonia in the right place, at the right concentration, in the right chemical form. In water systems, ammonia becomes an even sharper knife edge. Fish and microbial reactors can produce it continuously. Nitrifying bacteria can convert ammonia to nitrite and nitrate, but they require oxygen and stable pH. If that microbial community crashes, ammonia spikes and biology suffers first. Trace contaminants are the next layer, and they are not optional details. Plastics outgas, lubricants evaporate, and cleaning agents leave residues. Human bodies emit volatile organics, and industry adds solvents and particulates. In a sealed volume, trace compounds become chronic exposure. Picture a new module after installation, with fresh polymers and adhesives still curing. The air has a faint chemical edge, even if instruments say it is safe. In a terrestrial building, those compounds drift away through open windows and huge air exchange. In a ship, they circle back again and again. Air handling must therefore include more than CO2 scrubbing. It needs activated carbon, catalytic oxidizers, particulate filters, and sensors that do not drift. It also needs a replacement plan for media that saturates, degrades, or becomes biologically colonized. Catalytic oxidizers are often described as burning contaminants without flames. They use catalysts to convert volatile organics into CO2 and water at controlled temperatures. That helps, but it also creates more CO2 load for scrubbers. Every cleanup step pushes on another loop. Monitoring becomes a life support organ. Sensors must measure oxygen, CO2, humidity, ammonia, and a long list of organics. Calibration must be routine, because a sensor that lies is worse than no sensor. The ship must treat metrology as a cultural practice. Metrology sounds abstract, yet it is the difference between trend and surprise. A drifting CO2 sensor can hide a slow decline in scrubber performance. A humidity sensor that reads low can allow mold-friendly conditions to persist. The ship must teach measurement the way it teaches language, early, often, and with respect. The air loop also intersects with fire safety. In a habitat, oxygen fraction, pressure and materials determine flammability. Higher oxygen makes breathing easier, yet it makes fires faster and hotter. The ship must choose an atmosphere that balances physiology, engineering, and catastrophe risk. Historically, oxygen-rich atmospheres have been seductive and dangerous. Early spacecraft designs sometimes favoured higher oxygen for simpler systems. Tragedies and close calls taught that materials behave differently when oxygen rises. In a sealed ship, a small flame can become a chemical event. Now water, because water is where closure becomes brutally physical. Every person needs litres per day for drinking, hygiene, and food production. Agriculture multiplies that demand even when water is recycled. A ship must run a purification loop that never stops. Water is also the habitat's most convincing illusion. It looks clear, it tastes fine, and it can still be wrong. Dissolved organics are invisible, and microbes can hide in plumbing. In a closed world, trust in water must be earned continuously. ISS again offers a reference point. It recovers water from humidity, condensate, and urine, then polishes it for reuse. It still depends on replacement filters, spare pumps, and periodic intervention. A generation ship must make that loop self-renewing. The ISS system is a triumph of engineering, but it is not a planet. It can tolerate downtime because new parts arrive. It can tolerate inefficiency because Earth supplies margin. A generation ship must build a water system that can be repaired with what it already has. Water recycling is a stack of processes, not a single machine. Distillation separates volatiles, filtration removes particulates, and membranes reject salts and microbes. Catalytic oxidation breaks down organics that slip through, and ion exchange polishes the remaining trace chemistry. Each stage has a failure signature that the crew must learn to recognize. Distillation can carry over volatile contaminants if temperatures drift. Membranes can foul, raising pressure and lowering flow. Ion exchange resins can exhaust, then quietly release what they once captured. No loop is perfectly closed because losses hide in ordinary life. Water binds into biomass, leaves in waste and escapes in tiny leaks. It is trapped in filters, absorbed into materials and carried away in maintenance operations. Over centuries, small losses become a slow drought. Even the ship's air is a water reservoir because humidity is constantly moving. Dehumidifiers condense it, and that condensate becomes feedwater again. A malfunctioning condenser is not just comfort loss, it is water loss, corrosion risk, and microbial opportunity at the same time. Contamination is the other enemy because water is a microbial habitat. Biofilms grow in pipes, tanks, and membranes, and they resist cleaning. A biofilm can change flow, foul sensors, and shelter pathogens. It also becomes a chemical factory, producing acids and metabolites. Biofilms are not a thin slime you wipe away once. They are structured communities with channels, gradients, and protective matrices. Inside them, microbes can swap genes and tolerate disinfectants. A ship's plumbing can become a living organ that evolves its own defenses. Persistent organics are a long-term risk in closed water. Some compounds resist oxidation and accumulate at low concentrations. Pharmaceuticals, plasticizers, and industrial residues can cycle indefinitely. The ship must decide what to destroy, what to capture, and what to tolerate. That decision is partly toxicology and partly ethics. A trace compound that is harmless for a year may not be harmless for a lifetime. Endocrine-disrupting chemicals can act at very low concentrations. The ship must define safe across generations, not across missions. Microplastics are not only an Earth problem, where particles from fabrics, seals, and filters enter water and air. They can carry adsorbed toxins and provide surfaces for microbes. In a closed habitat, microplastics are a slow inventory that trends upward unless actively removed. Imagine a beam of light cutting through a maintenance bay. Dust motes drift like tiny satellites, and some of them are polymer fragments. They settle into filters and corners, then get disturbed and recirculated. The ship must treat dust as both nuisance and archive. Heavy metals are another quiet threat. Corrosion releases ions, and industrial processes can shed contaminants. Even low levels matter when exposure is lifelong. Water chemistry must therefore be controlled to reduce corrosion, while still supporting biology. Corrosion control becomes a balancing act between materials science and biochemistry. Adjusting pH and dissolved oxygen can slow metal loss. Yet those same parameters affect nitrifying bacteria and plant nutrient uptake. The ship's water is never just water, it is a chemical compromise. Replaceable media becomes a paradox in deep space. Filters and resins are consumables, yet consumables imply a finite timeline. The ship must either manufacture media, regenerate it, or design processes that do not rely on it. Each approach demands energy, complexity, and skilled labor. Regeneration sounds clean on paper, but it has costs that appear elsewhere. Thermal regeneration consumes power and produces waste heat. Chemical regeneration requires reagents that must themselves be made and purified. The ship is always paying, and it must choose the currency. Continuous monitoring is the only way to see slow failure. You need total organic carbon measurements, microbial counts, and spectroscopy for trace ions. You need trend analysis across years, not just pass-fail thresholds. A ship that cannot see drift will discover it too late. Trend analysis becomes a kind of story the ship tells itself. A rising line on a graph is an early warning, but only if someone is trained to care. In a long-lived habitat, boredom is a hazard. The most dangerous failures are the ones that look like routine. Water also links to thermal control and radiation shielding. Tanks can buffer heat and protect crew, yet warm water encourages microbial growth. Cold storage slows biology, yet it complicates plumbing and energy use. The ship must choose temperatures as an ecological decision. A tank placed near a sleeping module can double as shielding, because hydrogen-rich water blocks radiation better than many materials. That same tank can stratify, forming warm layers and cold layers. Stratification changes microbial growth and dissolved gas levels. The ship must mix and manage, not merely store. Food is where the biosphere problem becomes visible, because it must feed thousands. Calories are not abstract. They are daily mass flow, daily labour, and daily power consumption. A generation ship must run agriculture like a power plant and a hospital. Visually, the farm modules are the ship's green heartbeat. Rows of leaves glow under tuned LEDs, and condensation beads on piping. The air smells faintly of chlorophyll and damp substrate. It is beautiful, but it is also infrastructure. Start with the basic arithmetic. An adult needs roughly 2,000 calories per day, and a large population multiplies that into tons of biomass per year. You must also provide protein, fats, vitamins, and minerals. Malnutrition can be subtle, yet it erodes health and resilience. The arithmetic extends beyond calories into micronutrients and essential fatty acids. Vitamin deficiencies can appear slowly, then suddenly become social problems. Iron and iodine shortages can affect cognition and development. In a closed ship, nutrition is not personal choice, it is system design. Hydroponics offers control and efficiency. Nutrients are delivered directly in water, and growth can be rapid under optimized light. It reduces soil mass and avoids many soil pathogens. It also depends on pumps, sensors, and stable nutrient formulation. Hydroponic control means controlling ions like nitrate, potassium, calcium, and phosphate. It also means controlling electrical conductivity and pH, because roots are sensitive. A small dosing error can lock nutrients out, even when they are present. The plants then show stress like a silent alarm. Aeroponics pushes efficiency further. Roots hang in air and receive nutrient mist, reducing water use. It can produce high yields per area, and it allows precise oxygenation. It also introduces fragility, because nozzle clogging and pump failures can kill crops quickly. In aeroponics, minutes matter more than hours. If misting stops, roots dry and die fast under bright lights. That creates a maintenance culture of redundancy, alarms, and rapid response. The system is efficient because it is unforgiving. Soil-based systems offer different strengths. Soil buffers nutrients, hosts complex microbiomes, and can stabilize pH. It also stores water and supports diverse crops with fewer control systems. Soil is heavy, and it can harbor persistent pests and diseases. Soil is also history in a box. It contains organic matter, mineral particles, fungi and bacteria that interact in ways we still do not fully model. That complexity can stabilize yields when inputs vary. It can also surprise you with outbreaks, because life finds niches. Hybrid systems are likely, because no single method covers all needs. Hydroponics can provide leafy greens and fast cycles. Soil beds can support tubers, grains, and microbial buffering. Algae or microbial bioreactors can close nutrient loops and provide supplemental protein. The ship's farms may look like separate rooms, but they are coupled by pipes and schedules. Waste streams become nutrient streams. Plant residues become compost feedstock. The farm is not a garden, it is a metabolic organ with many chambers. Light is the hidden cost of artificial farming. Photosynthesis needs photons, and photons require power, heat rejection, and reliable fixtures. LEDs improve efficiency, yet they still turn most energy into heat eventually. The ship must budget agriculture as a major electrical load. Heat rejection is especially unforgiving in space, because radiators must dump waste heat into vacuum. Every watt used for light becomes a watt that must be moved and rejected. Farming therefore competes with propulsion, computing, and comfort. The ship must decide what it values when power is tight. The spectrum and photoperiod become operational variables. Different crops want different light recipes, and mistakes reduce yield. Light schedules also interact with human circadian rhythms and habitat heat loads. Farming becomes a systems engineering discipline. A red-heavy spectrum can drive photosynthesis efficiently, but plants also use blue light for morphology and stomatal behavior. Photoperiod affects flowering, fruiting, and nutrient content. In a ship, a software update could change a harvest. That is both power and vulnerability. Crop diversity is not a luxury, it is resilience. Monocultures maximize efficiency, yet they invite single-point biological failure. Diverse crops spread risk across species, pests, and nutrient demands. Diversity also supports nutrition and morale over long timelines. Morale matters because food is culture, not only fuel. A ship that eats the same starch and protein every day becomes psychologically brittle. Variety carries meaning, memory, and celebration. The biosphere must feed the mind as well as the body. Pollination is a design choice, not an assumption. Some crops self-pollinate, some need wind, and some need animals. You can use manual pollination, robotic assistance, or managed insects. Each option adds labour, complexity, and biosecurity concerns. Managed insects introduce a living subsystem with its own diseases and escape risks. Manual pollination introduces labour demands that scale with acreage. Robotic pollination adds parts, sensors, and maintenance. The ship must decide which form of complexity it prefers, biological or mechanical. Protein is the hardest macronutrient to scale cleanly. Plant protein is efficient, yet it can lack certain amino acid profiles without careful planning. Animal protein adds conversion losses, because feed becomes meat with low efficiency. The ship must choose protein sources as an energy decision. On Earth, livestock is supported by vast land, sunlight, and time. In a ship, feed is manufactured under lights, and every conversion step costs energy. That makes protein a thermodynamic question, not only a culinary one. The ship's menu becomes a power budget. Insects are often proposed because they convert feed to protein efficiently. They require less water and space than livestock, and they can eat certain waste streams. They also raise allergy risks, pathogen management issues, and cultural acceptance challenges. Insects also produce frass, which is both waste and fertilizer. That can help close nutrient loops, but only if pathogens are controlled. Processing, cooking, and storage must be standardized. In a closed habitat, food safety is not a regulation, it is survival. Aquaculture offers another path. Fish can provide high-quality protein and fats, and water systems can integrate with plant nutrient loops. It also demands careful control of ammonia, oxygen, and disease. A tank crash can be sudden and catastrophic. Aquaculture is visually serene until it fails. Water looks calm, fish glide in slow arcs, and aeration bubbles rise like beads. Then oxygen drops, and the system flips. The ship must monitor dissolved oxygen and nitrogen compounds like a heartbeat. Cultured meat is a future option with uncertain economics. It can reduce animal husbandry burdens, yet it requires sterile bioreactors, growth media, and energy. Sterility is difficult in a ship that is fundamentally a microbiome. The process may be reserved for supplements, not staples. Even if cultured meat becomes routine, it still depends on amino acids, sugars, and growth factors. Those inputs must be produced, purified, and protected from contamination. The ship may find that microbial protein is simpler, even if it is less familiar. Familiarity is not always the cheapest resource. Fermentation and microbial protein may be the most reliable protein backbone. Yeast, fungi, and bacteria can convert sugars or waste into edible biomass. They can run in controlled tanks with predictable yields. They also require strict contamination control and careful nutritional balancing. Fermentation is ancient technology, which is why it belongs here. Humans have used microbes to preserve food for millennia, long before we understood cells. On a generation ship, that history becomes engineering. The difference is scale, monitoring, and accountability. Food production is also a nutrient recycling problem. Human waste contains nitrogen, phosphorus, potassium, and trace elements. If those nutrients are lost, the ship slowly starves its soil and hydroponic solutions. Waste must become feedstock, safely and consistently. Phosphorus is especially important because it has no atmospheric reservoir like nitrogen. On Earth, we mine it and spread it on fields. In a ship, every gram must be recovered from waste, ash, and residues. Losing phosphorus is like losing time because recovery options are limited. Composting is simple, yet it is biologically complex. It relies on microbial communities that can shift with temperature and inputs. It can produce pathogens if mismanaged, and it can release ammonia and volatile organics. The ship must treat compost as a regulated reactor. A compost bay is not romantic in a sealed habitat. It is warm, damp, and alive, and it smells like decomposition even when it works well. Air handling must capture emissions, and operators must track temperature profiles. If it cools too much, pathogens can persist. Anaerobic digestion can recover energy as methane and stabilize waste. It can reduce pathogens and produce fertilizer streams. It also demands careful control of pH, temperature, and microbial balance. A digester upset can ripple into gas supply and nutrient availability. Digesters are ecosystems with their own succession, and they can be temperamental. A sudden change in feedstock can cause acid buildup, suppressing methane producers. Gas output drops, and the ship loses both energy and stability. The crew must treat the digester like a living colleague. Human waste processing intersects with social norms and governance. People must comply with sorting, hygiene, and protocols every day. If compliance falls, contamination rises, and the loop degrades. Closure is therefore partly a cultural achievement. This is where the mysterious tone deepens, because the ship is also an experiment in behaviour. The most elegant recycling system fails if people bypass it when tired. The smallest act of negligence becomes a chemical signature in the air. The ship learns its inhabitants, and it remembers. This leads to the central trade-off. Ecological stability is not the same as maximum efficiency. A system tuned to razor-thin margins can produce more food per watt. It can also collapse faster when a variable shifts. Efficiency reduces slack, and slack is what absorbs surprises. On Earth, oceans, forests, and deep soils provide enormous buffer capacity. In a ship, buffer capacity must be designed deliberately. Tanks, reserves, and redundant pathways become the ecological equivalent of savings. Buffers can be physical, like extra water volume and oxygen reserves. They can be biological, like multiple crops that mature at different times. They can be procedural, like slower ramp rates that avoid shocking microbial reactors. The ship must decide which buffers it can afford to carry. Biodiversity is a form of insurance. Multiple species can perform similar functions, so one failure does not end a process. Microbial diversity can stabilize nutrient cycling and resist invasions, yet diversity also increases monitoring complexity and unknown interactions. There is an uneasy truth here. A simplified ecosystem is easier to model, but it can be easy to break. A complex ecosystem can be harder to predict, but it may absorb shocks. The ship must choose how much uncertainty it can live with. Designers must choose where to allow messiness. Some compartments can be tightly controlled, like sterile bioreactors and medical zones. Other compartments can be more ecological, like soil beds and compost systems. The ship needs ecological fire breaks to prevent cascading failures. Fire breaks can be physical, chemical, and procedural. Separate air handling zones can prevent spores from spreading. Quarantine greenhouses can isolate new cultivars and test for pathogens. Waste streams can be sterilized before entering food production loops. A quarantine greenhouse is a visual statement of humility. It is a bright room behind sealed doors with its own tools and airflow. New plants grow there under observation, not trust. The ship cannot afford to be sentimental about biology. The ship must also plan for controlled loss, because waste can be stabilizing. A small reservoir of unused nutrients can prevent sudden shortages. A stored grain reserve can buffer crop failures and power outages. Redundancy in food is not only calories, it is time. Time is the resource that cannot be manufactured quickly. You can build a pump in a machine shop, but you cannot grow wheat overnight. Reserves convert time into options. Without them, every failure becomes urgent, and urgency breeds mistakes. Microbes are the chapter's hidden protagonist. The ship will be a microbiome, because humans carry microbes everywhere. Surfaces, air, water, and soil will host communities that evolve. The question is not whether microbes exist. The question is which ones dominate. Microbial dominance is shaped by humidity, temperature, and available nutrients. Filters and ducts can become selective environments, favouring certain species. Cleaning protocols can shift communities toward resistant strains. The ship is not neutral ground. It is a set of evolutionary pressures. Some microbes are symbionts, and they keep humans healthy. Gut microbiomes influence immunity, metabolism, and mental health. Skin microbes compete with pathogens and shape inflammation. A ship that disrupts microbiomes may create chronic disease without a single outbreak. Consider a child born on the ship, never exposed to earth soil or outdoor diversity. Their immune system will be trained by the ship's microbial library. That could be beneficial if curated well. It could also be narrowing if the ecosystem becomes too sterile or too uniform. Other microbes are opportunists. In a closed habitat, they exploit damp corners, filters, and nutrient-rich biofilms. They can degrade materials, clog systems, and produce toxins. They do not need to be dramatic to be dangerous. Material degradation is a quiet microbial power. Certain fungi and bacteria can digest plasticizers and adhesives. Others accelerate corrosion by creating acidic microenvironments. A ship's walls can become a food source in slow motion. Maintenance is therefore also ecology management. Pathogens are inevitable over centuries. Even if the ship launches with screening, mutations occur and immunity shifts. A mild virus can become severe in a naive population. A bacterium can acquire resistance under repeated antibiotic exposure. Population structure matters here, because a closed ship is a closed network. Pathogens do not need airports or cities. They need corridors, shared air, and shared surfaces. The same connectivity that makes society possible makes outbreaks efficient. Antibiotic resistance is a predictable evolutionary outcome. In a closed world, antibiotic use creates selection pressure with nowhere for genes to dilute. Resistant plasmids can spread across species in biofilms. The ship must treat antibiotics as a finite strategic resource. Biofilms are especially dangerous reservoirs for resistance. They allow slow growth, stress tolerance, and gene exchange. A drain line can become a genetic marketplace. The ship must monitor not only pathogens but also the environments that train them. That pushes medicine toward alternatives and prevention. Vaccination programs must be continuous and updated as pathogens evolve. Phage therapy may become a standard tool targeting bacteria with viruses that can be tailored. Immunomodulation and microbiome transplants may be routine, not experimental. Phage therapy is not magic either, because phages evolve alongside bacteria. A tailored phage can lose effectiveness as bacteria change receptors. That means the ship may maintain phage libraries and rapid screening labs. Medicine becomes a kind of ecological arms control. Microbiome management becomes an institution. The ship may maintain curated microbial libraries, like seed banks for bacteria. It may inoculate newborns with selected communities to preserve health. It may periodically reset certain environments with sterilization and controlled recolonization. A microbial library is a fascinating image. Vials in cold storage, labeled like a museum collection. Each strain is a tool and a risk. Some are used to start fermenters, some to stabilize compost, and some to restore gut health. The ship preserves life to preserve life. Quarantine is not an emergency measure, it is permanent policy. New plants, new animals, and even new machine parts can carry microbes. People moving between compartments can spread spores and biofilms. The ship must normalize isolation protocols without destroying social cohesion. Social cohesion is tested by routine inconvenience. Quarantine means delays, extra steps, and restricted movement. Over decades, those steps can feel like oppression, unless the culture understands the reason. The ship must teach microbiology as civic knowledge, not specialist law. Materials and design influence microbial ecology. Smooth surfaces resist biofilm attachment, yet they can still be colonized. Antimicrobial coatings degrade over time and can select for resistant strains. Plumbing geometry can create stagnant zones that become microbial reservoirs. Designers learn to fear dead legs in pipes, where flow is low and stagnation invites growth. They learn to avoid hidden cavities where condensation collects. They learn that a corner is not just a corner, it is a microclimate. Cleaning is not simple in a closed world. Harsh chemicals create air and water contaminants that must be removed. Heat sterilization consumes power and stresses materials. Ultraviolet light can disinfect surfaces, yet it has shadows and limits. The ship must balance cleanliness with chemical and energy budgets. Even the smell of cleaning becomes a systems issue. Solvents and fragrances linger, then circulate into filters and water condensate. The ship must prefer methods that do not create new contaminants. Cleanliness must be designed, not improvised. Now consider how small failures become existential. In a closed habitat, shocks propagate through coupled loops. A crop failure is not only food shortage. It can reduce oxygen production, increase CO2, and raise stress, which then reduces maintenance quality. Coupling is the hidden architecture of risk. The air loop depends on the farm depends on water purity depends on filters and power depends on thermal control, and thermal control depends on water. The ship is a circle of dependencies. A CO2 spike can begin as a minor scrubber degradation. A sensor drifts, a filter saturates, and the system compensates until it cannot. People become fatigued and irritable at levels that still seem safe. Decision-making worsens, and the ship enters a feedback loop of human error. CO2 affects the body in subtle ways before it becomes an emergency. Sleep quality declines, headaches appear, and attention narrows. Those are exactly the conditions that produce maintenance mistakes. The ship must treat slightly elevated as a serious operational state. A nutrient loop break can start with a microbial shift in a bioreactor. pH drifts, a community collapses, and output quality changes. Crops show deficiency symptoms weeks later, when reserves are already spent. The delay hides the cause, and the response arrives late. Deficiency symptoms are visual, but they are not specific. Yellowing leaves can mean nitrogen shortage, iron lockout, or root stress. That ambiguity costs time, and time is the scarce resource. Diagnostics must be fast, and spare pathways must already exist. A single fungus can become a ship-wide crisis. Spores hitchhike on clothing, tools, and airflow. A monoculture greenhouse provides perfect conditions, and infection spreads faster than replanting can recover. The crew faces a choice between aggressive sterilization and preserving the rest of the ecosystem. That choice is never clean. Sterilization can save the farm, but it can also disrupt beneficial microbes. It can introduce chemical residues that must be filtered. It can force a temporary shutdown that changes oxygen production. The ship must decide what to sacrifice to save the whole. Scenario building becomes part of survival planning. The ship must rehearse biosphere emergencies like sailors rehearse storms. It must model cascading failures across air, water, food, and health. It must also plan for the social consequences of rationing and quarantine. Rehearsal is also education across generations. The people who designed the system will not be alive to explain it later. Procedures must be taught, practiced, and updated. The ship must preserve institutional memory as carefully as it preserves oxygen. In these scenarios, time is the real weapon. A disease outbreak can double in days, while a crop cycle takes weeks. A water contaminant can spread in hours, while replacement media takes months to manufacture. The ship must store time as reserves and redundancy. Stored time can look like extra seed stock, extra nutrient salts, and spare membrane modules. It can look like a second digester running at low load, ready to take over. It can look like empty tank volume reserved for emergencies. These are not luxuries, they are survival margins. The biosphere also changes as the ship ages. Trace contaminants accumulate in unexpected sinks like dust, filters, and sediments. Microbial communities adapt to the habitat's chemistry and temperature. The system can drift into a new equilibrium that is stable, yet unhealthy. A stable but unhealthy equilibrium is the most unsettling outcome. Nothing breaks dramatically and alarms do not sound. People simply feel worse, crops yield less, and maintenance becomes harder. The ship must learn to fear slow decline more than sudden failure. Even success has a cost. A tightly controlled ecosystem can become brittle because it excludes variability. A more natural ecosystem can be resilient, yet it can harbour hidden pathogens and pests. The ship must choose a philosophy of control, then live with its consequences. That philosophy will be debated like politics because it affects daily life. Do you allow a little microbial wilderness, trusting ecology to buffer shocks? Or do you pursue sterility, trusting sensors and protocols? The ship must answer, then keep answering, as evidence accumulates. This chapter's hardest truth is that closure is not a one-time achievement. It is a continuous negotiation between physics, biology, and maintenance attention. The ship must keep cycling molecules, while also cycling knowledge across generations. Knowledge is itself a consumable, because it decays without practice. A procedure that is not used becomes folklore. A warning that is not experienced becomes superstition. The ship must institutionalize curiosity, because curiosity catches drift before crisis. So the central question sharpens: could a self-contained generation ship sustain a stable population and functioning ecosystem for centuries? Or does the biosphere drift toward failure, one tiny imbalance at a time? The question is not only technical, because the ship is not only a machine, it is a living system that includes human attention and human fatigue. How many small chores can a society perform forever without cutting corners? How many alarms can it hear before it stops listening? We end where the engineering meets the human. A ship can recycle water, and it can scrub air, and it can regrow food. The next question is whether it can recycle trust, meaning, and social stability for centuries. Even if the ecosystem holds, people must hold. From here, the story turns from ecological loops to the minds that must run them. The hull can be strong, and the engines can be clever, yet the true payload is biology. Chapter 3 treated molecules as budgets, where every atom must be counted and reused. Chapter 4 treats people as a population genetics experiment, sealed under cosmological isolation, with no migration, no fresh genes, and no second chances. A generation ship is not one family line travelling together, holding hands through the centuries. It is a breeding population with rules, bottlenecks, and long-term arithmetic that never stops. The central question tightens here, like a pressure seal being torqued down. Could a closed human population stay healthy for centuries, or does it drift, quietly, statistically, toward extinction? Start with the idea of minimum viable population, which sounds like a headcount written on a clipboard. In practice, the key number is effective population size, not the census total. Effective size measures how many people actually contribute genes across time, across sex ratios, and across the variance in family size. In population genetics, effective size is the population that would behave the same way under idealized conditions. Those conditions are simple on paper: random mating, equal numbers of breeding males and females, and similar numbers of children per parent. A ship will never be ideal because ships are built out of schedules, hierarchies, and human preference. The result is that the genetic population can be much smaller than the visible crowd. A ship can carry 10,000 bodies and still have a small effective population. If a few lineages dominate reproduction, genetic diversity collapses faster than the crowd suggests. If many adults never reproduce, the gene pool shrinks without anyone noticing, until the consequences appear in clinics and nurseries. Picture the habitat ring from above, a bright band of light turning in darkness. The corridors look busy, the farms look green, and the classrooms look full. Yet the genetic future might be carried by a narrow subset of families, like a river forced through a thin channel. The ship can feel populous while its heredity becomes sparse. Effective size is reduced by unequal sex ratios, reproductive skew, and social stratification. It is reduced by age structure shocks, like a cohort lost to accident or disease. It is reduced by policies that seem fair, yet concentrate births into a narrow slice of the population. Even subtle causes matter, because genetics integrates small biases over long time. If one department has a culture of early parenthood, its lineages expand across generations. If another department delays reproduction for training, its genetic footprint shrinks, even if it keeps the ship alive. The ship's social design becomes a genetic force, whether anyone intends it or not. The ship therefore needs a population model that lives beside the life support model. It must track births, deaths, and the distribution of parenthood, not only the total count. It must treat demography as maintenance, because demography sets the future's genetic options. On Earth, migration and intermarriage can repair local bottlenecks over time. A village that loses diversity can be replenished by newcomers, even if no one plans it. A ship has no such background flow, and that absence changes everything. In a sealed world, every demographic choice becomes a permanent entry in the genetic ledger. Inbreeding is the first hard limit people recognise, yet it is often misunderstood. Inbreeding is not only cousin marriage, or a scandal in a family tree. It is the probability that two gene copies share a recent ancestor, rising steadily in small, closed populations. The inbreeding coefficient climbs each generation when the effective size is small. Even with strict rules against close relatives, distant relatedness accumulates. After many generations, everyone becomes everyone's cousin in the genetic sense, because the ship's ancestry is a closed loop. This accumulation is not a moral failure, and it is not a personal choice. It is a mathematical property of finite populations, like compound interest working in reverse. Each generation samples from the last, and sampling creates overlap. The smaller the effective size, the faster the overlap becomes universal. Inbreeding increases homozygosity, which reveals recessive harmful variants. Some effects appear as infant mortality or congenital disease, sharp and visible. Others appear as reduced fertility, immune weakness, and lower resilience under stress, slow, ambiguous, and easy to misattribute. The danger is not only a single dramatic disorder that everyone can name. The danger is a broad shift in health statistics, where many small vulnerabilities add up. A slight drop in sperm count, a slight rise in miscarriage, a slight increase in infection severity. Over centuries, those slight shifts can become the ship's baseline. Genetic drift is the quieter partner to inbreeding, and it acts even without harmful genes. Drift is random change in allele frequencies, stronger when effective size is small. Over time, drift fixes some variants and deletes others, regardless of usefulness. Drift matters because it erases options, and options are what evolution spends. A trait that might help later can vanish early by chance, like a tool dropped into the void. A mildly harmful variant can become common, not because it is selected, but because randomness is stronger than selection. On Earth, drift is most dramatic in island populations and founder events. History has examples, from isolated valleys to remote archipelagos, where certain genetic diseases became common. Those cases are warnings written in blood chemistry, and the ship is the most extreme island imaginable. This is why a few hundred is not automatically safe across centuries. A few hundred might survive a few generations with careful matching and good luck. Over dozens of generations, drift and inbreeding compound, and the ship becomes genetically narrower. The narrowing can be invisible until a crisis demands traits the population no longer has. Selection still operates, but it is selection inside an artificial world. The ship's environment is stable in some ways and harsh in others, like a climate that never changes yet never forgives. Traits that help in a rotating habitat under recycled air might be favoured, even if they harm later planetary life. Consider the physiology of living under rotation, where gravity is a centripetal trick. The vestibular system adapts, bone remodeling responds to load, and cardiovascular regulation settles into a new normal. If the ship's gravity is lower than Earth's, even by a fraction, selection pressures can shift subtly. Over time, the population may become optimized for the ship, not for the destination. Selection can also be cultural rather than biological, yet the genes still ride along. If certain jobs confer status and larger families, genes correlate with social position. If certain groups delay reproduction for training, their lineages shrink, even if they are essential. Culture becomes a sieve that sorts heredity. So the ship faces a design choice that is also a moral choice. Does it accept drift and hope medicine compensates? Or does it actively manage reproduction as a core system, like air and water? Reproductive governance begins with a simple coupling. Population size is constrained by food, oxygen, water, and heat rejection. If births exceed capacity, the ship does not merely get crowded, it destabilizes the biosphere loops that keep everyone alive. In a closed habitat, every additional person is a permanent metabolic load. They eat, breathe, excrete, and shed microbes, and those outputs must be processed. The life support system is a set of linked feedback loops, and population is the strongest driver. When the driver changes too fast, the loops overshoot. Overshoot is a classic ecological failure mode, and a ship has no external buffer. A temporary surplus of births can create decades of elevated demand. That demand can force farm expansion, power increases, and higher waste loads, which then raise failure risk. Even if the ship has advanced automation, biology is not instant. Crops need time to grow, soil analogues need time to stabilize, and microbial reactors need time to adjust. A sudden baby boom is not just more mouths, it is a step change in planning horizons. The ship can survive the first year, then fail in the 10th. Undershoot is also dangerous because it breaks age structure and labour capacity. Too few children means too few technicians later, and too few caregivers later still. Too few births can also reduce effective population size, accelerating genetic problems. The ship can become both understaffed and genetically fragile at the same time. The ship therefore needs a target population trajectory, not a fixed number. It needs a stable age pyramid that supports care, education, and maintenance labour. It needs slack for accidents, outbreaks, and cohort losses. A stable pyramid is not only about numbers, it is about timing. Training a surgeon, a reactor engineer, or a microbial ecologist takes years of mentorship and practice. If a cohort is missing, the skill pipeline breaks, and the ship becomes dependent on fewer experts. Dependency is a form of fragility that looks like efficiency until it fails. Birth quotas are the blunt instrument most concepts propose. A quota can be annual, cohort-based, or resource-triggered. It can be tied to calories, oxygen margin, or habitat volume. It can also be tied to genetic goals, like maximizing diversity. Quotas sound clinical, yet they're often implemented through ordinary bureaucracy. Forms, waiting lists, eligibility criteria, and appeals boards. The mundane machinery of administration becomes the interface between private desire and public survival. In a sealed world, paperwork can decide who exists. Quotas create immediate ethical tension. Autonomy is central to human identity, and reproduction is not a trivial preference. Yet the ship cannot allow unlimited choice without risking system collapse. The mathematics of survival competes with the politics of consent. The tension is sharpened by time because consequences are delayed. A decision to exceed capacity might not kill anyone today, and that makes it tempting. The penalty arrives later, as thinner safety margins and cascading maintenance debt. The ship's ethics must therefore include responsibility to people not yet born. Some ships might use licensing, where parenthood requires meeting health and training criteria. Others might use lotteries, where births are allocated randomly to avoid class capture. Others might use incentives, where resources and status reward compliance. Each method shapes society differently. Licensing can drift toward credentialism, where the educated reproduce and the marginalized do not. Lotteries can feel fair, yet they can also feel arbitrary, like fate administered by committee. Incentives can work quietly, but they can also create a market where children become tokens. Every approach creates enforcement questions. A rule without enforcement becomes a suggestion. Enforcement without legitimacy becomes coercion that corrodes trust. The ship must decide what it is willing to be long before the first quota is tested. Enforcement is not only police action, it is also surveillance and record-keeping. Pregnancy detection, medical confidentiality, and the control of contraception become political technologies. The ship's clinics become sensitive spaces, where care and authority overlap. Even the design of doors and data systems becomes part of governance. Age structure is the second governance lever, and it is less visible than quotas. If people reproduce too early, dependency ratios rise and training pipelines strain. If people reproduce too late, fertility drops and genetic contribution narrows. Human fertility is not a smooth curve, and the ship cannot pretend it is. Female fertility declines with age, male fertility changes too, and pregnancy risks rise over time. If the ship pushes parenthood late to reduce short-term load, it may pay later in infertility and medical complexity. A policy that looks efficient can become self-defeating. Spacing matters because the ship's ecosystem responds to load changes. A baby boom increases food and medical demand immediately. It increases housing and education demand for decades. The ship must smooth berths to keep life support within stable operating ranges. This smoothing can be done through scheduling, but scheduling touches intimacy. It turns family planning into a public calendar, and that can feel intrusive. Yet without smoothing, the ship gets waves. Waves of diapers, then schools, then apprenticeships, then retirements. Waves are hard on any system, and lethal in a closed one. This is where demography becomes operational planning. The ship schedules births the way it schedules reactor maintenance. It treats the population as a dynamic load, not as a static community. That framing is efficient, and it is also chilling. The chill comes from the language of systems engineering, where human beings become variables. It can be tempting to hide behind that language because it reduces moral pain. Yet the ship cannot afford denial, because denial produces backlash. A sustainable policy must be both mathematically sound and emotionally survivable. Genetic management strategies promise a way out of the small population trap. The simplest is to start with a larger effective population than the visible crew. Cryopreserved embryos and gametes can expand the gene pool across centuries. A cryobank acts like an external continent of diversity stored inside the hull. It can inject new alleles when drift narrows the population. It can also reduce the need for coercive mating rules, because genetic variety is available by design. Visually, it is a quiet vault behind thick insulation, racks of sealed canisters sleeping in blue-white cold. Each sample is a compressed biography, a potential person waiting for a future that cannot speak their name. The bank is both a medical resource and a symbolic archive. It says in hardware that the ship planned for genetic time, but a cryobank is not a magic reset. It requires long-term cold storage, reliable power, and stable containers. It requires records that remain interpretable across language drift and institutional change. It requires trust that the bank is used fairly. Power reliability is not a footnote, because cryogenic failure is irreversible. A short warming event can destroy viability, and the loss might not be discovered until decades later. The ship must therefore build redundancy, alarms, and maintenance rituals around the bank. The cryobank becomes a system that needs its own life support. Records are equally fragile because meaning decays even when paper survives. Labels must outlast software formats, and metadata must outlast political regimes. Who donated, what screening was done, and what consent was given must remain legible. Otherwise, the bank becomes a box of unknowns that nobody dares to use. Rotating lineages is another strategy, where reproduction is planned to equalize family sizes. The goal is to reduce variance in reproductive success, increasing effective size. This can be done through pairing guidance, birth allocation, or social norms that discourage very large families. Variance is the hidden killer of effective population size. If some parents have 6 children and others have none, the genetic future becomes lopsided. Equalizing family size spreads genetic representation, like balancing weight across a rotating ring. It is not romantic, but it is stabilizing. Pairing guidance can be advisory, where people choose within recommended bounds. It can be mandatory, where mating is assigned to maximize genetic distance. Mandatory assignment is efficient on paper, yet it risks rebellion and black market relationships. The advisory version relies on education and social buy-in. People must believe that genetic distance matters and that the system is not rigged. The mandatory version relies on authority, and authority has a half-life. Over centuries, a rule that feels unnatural can become a spark for factional identity. Genetic screening can reduce the burden of severe recessive disease. Carrier screening can guide pairings or embryo selection. It can also become a tool of stigma, where certain lineages are labelled risky and quietly excluded. Screening is powerful because it converts invisible risk into visible categories. A person who feels healthy can be told they carry a harmful variant, and that knowledge changes how others see them. The ship must therefore decide how to handle confidentiality, disclosure, and consent. A medical tool can become a social sorting mechanism. Embryo selection can lower disease risk, yet it can also narrow diversity if overused. If the ship selects for a small set of optimal traits, it reduces variance that might be useful later. Optimization can become a genetic monoculture, which is brittle under surprise. The temptation to optimize is strong in a closed world because every problem feels permanent. If a trait correlates with fewer medical emergencies, the argument writes itself. Yet evolution's lesson is that today's advantage can be tomorrow's weakness. The ship needs diversity not because it is beautiful, but because it is insurance. Gene therapy is the most powerful and the most uncertain tool. In principle, it could correct harmful variants and manage mutation load. In practice, it requires deep expertise, manufacturing capacity, and long-term monitoring of off-target effects. Gene therapy also changes the meaning of inheritance. If edits are heritable, the ship is redesigning its descendants. If edits are somatic, the ship must treat therapy as routine healthcare. With supply chains and quality control, heritable edits raise questions that do not expire. Who approves a change that will persist for centuries? What counts as disease, and what counts as preference? If the ship edits away a variant that seems harmful, it may also remove a protective effect that nobody understood. Biology is full of trade-offs that only appear under different environments. The ship must also guard against governance capture through genetics. A ruling group could privilege its own lineages under the language of health. A well-meaning committee could drift into eugenics by incremental policy. The genetic program becomes a political instrument, whether intended or not. Incremental drift is the danger because each step can seem reasonable. A screening program becomes a recommendation, then a requirement, then a prerequisite for social status. The ship might never announce a new ideology, yet it can still build one. Power often arrives wearing the mask of safety. Disease and immunity become the next century-scale constraint. A closed ship reduces exposure to Earth's diverse pathogens. That sounds like safety, yet it also changes immune training across generations. Immune systems adapt to the microbial environment they actually experience. On Earth, immune systems are shaped by constant low-level encounters. Many exposures are harmless, yet they teach the immune system what to tolerate and what to attack. In a cleaner, narrower microbial world, the immune system's calibration can shift. The result can be more allergies, more autoimmune tendencies, or simply different patterns of vulnerability. In low-diversity pathogen environments, some immune responses may become less robust. Allergies and autoimmune patterns can shift, Because immune regulation depends on exposure history, the ship's microbiome becomes the main teacher, and its lessons may be narrow. At the same time, the ship cannot become sterile. People carry microbes, farms carry microbes, and water systems grow biofilms. A closed habitat becomes a stable microbial ecosystem where certain strains can persist for centuries. Imagine the ship's plumbing in cross-section, a warm network where thin films of bacteria cling to surfaces. Imagine hydroponic trays where roots and microbes exchange nutrients in a controlled dance. These microbial communities are not villains, they are infrastructure. Yet infrastructure evolves, and evolution does not care about human comfort. Persistent strains can evolve alongside the population, creating a co-evolved disease landscape. A mild virus can become endemic, shaping childhood immunity. A bacterium can slowly accumulate resistance under repeated antibiotic use. The ship's medical history becomes part of the microbe's selective environment. Every course of antibiotics is a pressure, every disinfectant is a filter. Over decades, the microbial ecosystem can shift towards strains that tolerate the ship's routines. The ship may find itself living with organisms that are perfectly adapted to its corridors. The arrival problem is the most unsettling. After centuries, the crew may meet a planetary biosphere with unfamiliar pathogens and allergens. Their immune systems may be naive to local microbes. The first year after arrival could be a medical bottleneck, not a celebration. The scene is easy to romanticize: a hatch opening, sunlight, wind, and the smell of soil. Yet biology can turn that moment into triage. A harmless local fungus can trigger severe reactions, and a minor parasite can spread through a naive population. The ship might reach its destination only to face its most dangerous epidemic. So some designs propose controlled pathogen exposure over time, like an immune training program. Others propose maintaining microbial libraries and vaccines for anticipated threats. Both approaches require forecasting biology, which is notoriously hard. Forecasting is hard because ecosystems are contingent. Pathogens evolve, hosts evolve, and environments change in ways that models miss. The ship can prepare broadly, yet it cannot preload immunity to every possible world. That uncertainty is not a failure of planning, it is a property of life. Medical knowledge must also survive the same time horizon as the ship. Textbooks decay into outdated practice unless continuously taught and updated. A generation ship needs medical education as an institution, not as a stored archive. Knowledge is not a file, it is a living practice. Surgical skill requires hands-on repetition. Diagnostic skill requires pattern recognition. And scientific skill requires a culture of questioning. If the ship treats medicine as a library problem, it will discover too late that the library cannot intubate a patient. The ship needs apprenticeships, exams, and peer review, generation after generation. Pharmaceutical manufacturing is a parallel constraint. Stockpiles expire and resupply is impossible. The ship must synthesize drugs, culture biologics, and maintain quality control with limited reagents. It must also avoid contamination in a habitat that is never truly clean. Manufacturing is not only chemistry, it is logistics and standardization. Reagents must be produced or recycled, instruments must be calibrated, and protocols must be followed without drift. A minor error in purity can become a major error in dosing. In a closed world, a contaminated batch is not just a recall, it is a systemic shock. Antibiotics are a special case because resistance is predictable. The ship must treat antibiotics as strategic assets, using stewardship and alternatives. It may rely on phage therapy, narrow-spectrum drugs, or microbiome interventions to reduce selection pressure. Stewardship requires discipline, because the temptation is always to prescribe broadly. In a small population, an outbreak feels personal, and that pressure can lead to overuse. Yet overuse trains bacteria, and bacteria learn quickly. The ship must balance immediate relief against long-term efficacy, which is another kind of moral arithmetic. Now, radiation returns not as acute sickness, but as genetics. Chronic exposure increases mutation rates in germ cells as well as somatic cells. Over centuries, even small increases in mutation load can matter, because selection and drift interact. Space is not empty, and the ship moves through a thin rain of high-energy particles. Galactic cosmic rays can punch through material, leaving tracks of ionization. Solar particle events can spike the dose in hours, forcing people into storm shelters. Even with shielding, some radiation becomes part of daily life. radiation-induced mutations add to the baseline burden of harmful variants. In a large population, selection can remove some of that burden over time. In a small population, drift can fix harmful variants, and inbreeding can reveal them. The ship's genetic health becomes a long experiment in error accumulation. Shielding reduces dose, yet shielding is never perfect. Storm shelters handle spikes, but the background remains. The ship must treat genomic health as routine maintenance, like checking filters and seals. That implies surveillance. Regular sequencing can track mutation accumulation, carrier frequencies, and emerging risks. It can also become a privacy flashpoint, because genomes reveal family ties, disease risks, and ancestry. Sequencing can be framed as preventive care, and it can save lives. Yet it also creates records that can be misused, intentionally or accidentally. A genome can reveal non-paternity, hidden adoption, or predispositions that change social standing. The ship must decide who can see what, and for what purpose. Surveillance also raises governance questions about action thresholds. When does a variant frequency trigger intervention? Who decides which risks justify embryo selection or therapy? The ship needs a constitution for genetics, not only a lab. A constitution is needed because science does not tell you what to value. It can estimate probabilities, but it cannot define fairness. It can predict disease risk, but it cannot decide whose risk counts more. In a closed world, those decisions cannot be postponed, because postponement is itself a policy. Psychology and culture become the final inheritance system, and it evolves faster than genes. Values, taboos, and myths can become adaptive, because they stabilize behavior under constraints. They can also become destructive, because they can lock the ship into bad equilibria. Culture is a control system built out of stories. It tells people what is sacred, what is shameful, and what is worth sacrificing for. In a habitat where survival depends on cooperation, certain norms will be selected for because they reduce conflict. Yet selection does not guarantee wisdom, only persistence. A taboo against waste can protect resource loops, yet it can also punish necessary experimentation. A myth of mission purity can sustain discipline, yet it can also justify coercion. A culture of secrecy can prevent panic, yet it can also hide failures until they cascade. Cultural evolution is shaped by selection pressures inside the hull. Crowding, scarcity, and risk favor conformity and rule following. Long stability can favor complacency and loss of technical urgency. The ship is a petri dish for governance styles. Visualize a corridor mural painted by children who never saw Earth. The stars outside are not destinations. They are wallpaper, and the ship is the only world that feels real. In that world, a maintenance checklist can become a ritual, and a quota can become a taboo. The boundary between engineering and meaning blurs. Children born aboard inherit not only genes, but also narratives about why the ship exists. If the destination is abstract, the mission can become legend. A legend can motivate, yet it can also detach from operational reality. What happens when the destination becomes a metaphor instead of a coordinate? What happens when the ship's founding story is retold as myth, with heroes and villains? The risk is not that people forget the mission entirely. The risk is that they remember it incorrectly and act on a story that no longer matches the ship's needs. The ship must therefore manage meaning as carefully as it manages oxygen. It must keep the mission legible, measurable, and emotionally real. It must also allow personal lives that are not only service to the plan. If every joy is framed as duty, people will eventually reject duty. If every sacrifice is demanded without explanation, people will invent their own explanations. The ship needs space for art, love, and dissent, because those are pressure valves. Without pressure valves, pressure finds cracks. Education becomes the bridge between biology and governance. People must understand why quotas exist, why screening exists, and why maintenance rituals matter. If the system is opaque, compliance decays, and black markets appear. Education must be more than slogans, because slogans do not survive crises. People need mental models, not just rules, so they can improvise when conditions change. They must understand feedback loops, genetic drift, and the logic of redundancy. In a sealed world, scientific literacy is not prestige, it is safety. Black markets in reproduction are not a science fiction detail. They're a predictable response to coercive constraints. Hidden pregnancies, falsified records, and unreported relationships can destabilize both genetics and life support planning. A hidden pregnancy is not only a social violation, it is a systems violation. It shifts resource demand without warning, and it bypasses genetic planning. If enough people do it, the ship's model becomes fiction, and the ship begins to fly blind. The danger is not the individual act, it is the loss of predictability. Social trust is therefore a life support parameter. Trust determines whether people report illness early. Trust determines whether people follow quarantine. Trust determines whether people accept limits on reproduction without sabotage. Trust is built through transparency and fairness, yet it is destroyed by hypocrisy. If leaders exempt themselves from quotas, the system becomes illegitimate overnight. If genetic policies are applied unevenly, resentment becomes hereditary in its own way. The ship must guard legitimacy like it guards pressure integrity. A closed ship also amplifies conflict because exit is impossible. Disputes over quotas and genetic policy are not academic. They are disputes over whose children exist and whose line ends. On Earth, conflict can diffuse through migration, separation, and the slow forgetting of distance. On a ship, conflict circulates in the same air year after year. A feud can become a tradition, and a grievance can become a curriculum. The ship must therefore treat conflict resolution as infrastructure. The ship can try to reduce conflict through transparent rules and shared sacrifice. It can also try to reduce conflict through force, surveillance, and punishment. Force can work short-term, yet it often damages legitimacy, which is needed long-term. Surveillance can catch violations, but it also changes how people feel in their own homes. Punishment can deter, but it also creates martyrs and underground networks. The ship must decide whether it wants compliance or commitment. Commitment is harder to build, yet it is the only thing that scales across centuries. This chapter's mathematics keeps returning to the same theme. Small numbers behave differently than large societies, and time magnifies every bias. A stable-looking population can be drifting toward genetic fragility, even while daily life feels normal. Normality is not evidence of safety, because genetics moves quietly. The first signs may be statistical, not dramatic, showing up as small shifts in health outcomes. A committee can argue about whether the change is real, while the change continues. The ship needs the humility to treat weak signals seriously. So the ship needs buffers in people, not only in water and food. It needs enough effective population to absorb accidents and drift. It needs enough governance legitimacy to enforce constraints without breaking cohesion. Buffers can be designed, yet they must be maintained. A cryobank is a buffer, but only if it remains viable and trusted. A diverse breeding plan is a buffer, but only if people participate honestly. Even cultural norms are buffers, but only if they adapt rather than fossilize. It also needs humility about optimization. The urge to perfect the population can erase diversity and create brittle dependence on assumptions. The ship must preserve options, because it cannot predict the environment it will face at arrival. Ask the uncomfortable question that engineers avoid. What if the destination world is colder than expected, or hotter, or biologically hostile? What if the ship arrives damaged, and the first-generation planet side must live with scarcity again? In those scenarios, genetic and cultural flexibility matter more than any single optimized trait. We end with the transition that haunts every technical plan. Numbers and genes can be managed on paper, and even corrected with biotechnology. The ship's true unknown is governance. Who decides, who enforces, and what happens when the mission becomes a legend instead of a plan. From here, the story turns from population arithmetic to power and authority. The next chapter asks how a sealed world governs itself, when survival requires rules that feel like destiny, and when destiny is enforced by people. The hull can be strong, and the engines can be clever, yet the true payload is biology. Chapter 3 counted molecules, and Chapter 4 counted genes, yet both depend on a third ledger. That ledger is legitimacy, because every closed-loop system is also a closed-loop society. A generation ship is not only a vehicle crossing distance, it is a nation that cannot expand, cannot trade, and cannot exile problems into distance. The central question tightens again, because time turns small errors into permanent traditions. Could a self-contained ship sustain stable institutions for centuries, or does politics become the first irreversible leak? Visually, the ship looks like engineering, yet it feels like weather. Corridors breathe with ventilation pulses, bulkheads hum with power conversion, and the light has a curated spectrum that never quite matches a sun. The air is filtered, but it still carries faint signatures: ozone near power trunks, wet soil near gardens. People move through it like citizens in a city, but the city is also a machine. Every door is a seal, every garden is a reactor, and every argument has an oxygen cost. Start with the founding moment, because it sets the moral physics. A launch constitution is written by people who can still imagine Earth as a reference, with courts, elections, and rights that feel timeless. They can point to oceans and continents, even if only in memory, and say, "This is what normal looks like." They also write under pressure, because launch deadlines compress debate and reward clean slogans over messy edge cases. 2 centuries later, no living person remembers Earth as home, and the Constitution becomes an artifact. That artifact will still be quoted, but it will be quoted like scripture, selectively and sometimes strategically. A clause about public safety can expand, because safety in a pressure vessel is a persuasive word. A clause about freedom of movement can shrink, because movement is also access to valves and hatches. The text does not change, yet its interpretation drifts as the ship's ecology and technology drift. The ship must decide whether it is governed by a fixed text or by a living charter that can evolve. That choice is never purely philosophical, because it shapes how people treat failure. If the rules are sacred, then mistakes are blamed on people. If the rules are fluid, then mistakes are blamed on the rules. Rigid constitutions offer predictability, which is a form of safety in a sealed habitat. Predictability reduces rumour, because people can anticipate consequences and plan their lives without guessing the mood of leaders. It can limit impulsive rule changes during panic, and it can constrain leaders who claim necessity. In a crisis, that constraint is not abstract. It can prevent a desperate majority from voting away someone else's oxygen. Predictability also stabilises the ship's planning horizon, which is a technical variable as much as a political one. Crop cycles, spare part lead times, and maintenance windows all depend on schedules that cannot be rewritten weekly. When governance is stable, engineers can design around known constraints instead of guessing what will be permitted next year. In a closed habitat, uncertainty is not exciting. It is a load on every system margin. Rigid rules also risk becoming wrong in slow motion as technology, ecology, and demographics drift. A regulation written for one crop mix may fail when the microbiome in the grow beds shifts. A safety margin designed around one power architecture may become irrelevant after upgrades. A rule that once protected life support can later block adaptation, and the ship pays in brittle failure. Biology makes rigidity especially dangerous, because living systems evolve even when humans prefer stillness. Microbial communities in bioreactors can change under subtle selection pressures, temperature tweaks, trace contaminants, even a new disinfectant protocol. A policy that assumes a certain nitrifying efficiency can become quietly false, and the falsehood accumulates like scale in a pipe. When the failure finally appears, it looks sudden, yet it was growing for years. Adaptive charters offer flexibility, which is also a form of safety when conditions change. They can incorporate new engineering realities, new medical knowledge, and new social needs as the habitat matures. Over centuries, even the definition of emergency evolves, because the ship learns which alarms are survivable. Yet flexibility also invites capture, because flexibility can become a weapon in the hands of a charismatic faction. If rules can be rewritten easily, then power concentrates around whoever controls the rewriting. That control might be formal, like a council that schedules votes. It might be informal, like a media guild that frames what counts as reasonable. In closed societies, narrative is infrastructure. Whoever maintains it can quietly reroute the future. The ship therefore needs a design philosophy for governance that lasts longer than any personality. Separation of powers becomes a life support feature, not a political luxury. Operational authority must exist, because emergencies do not wait for debate or consensus rituals. Oversight must exist, because emergency authority is the easiest doorway to permanent rule. History offers a warning, even if the ship has only archives of it. On Earth, republics often failed not from invasion, but from internal exceptions that never ended. Temporary committees became permanent, wartime powers became peacetime habits, and fear became a renewable resource. In a generation ship, fear is even more renewable, because the walls never stop being thin. Earth's history also shows how institutions decay through convenience, not only through malice. Leaders learn that small shortcuts are rewarded, because shortcuts feel efficient during stress. Citizens learn that attention is tiring, and that delegation is soothing, until delegation becomes surrender. The ship inherits those human tendencies, and it amplifies them with confinement. A stable design splits functions that naturally conflict. One body sets long-term policy and resource budgets, tied to measurable system margins and published thresholds. Another body executes operations with clear limits and audit trails that cannot be quietly erased. A third body adjudicates disputes, because unresolved conflict becomes sabotage in a closed world. The adjudicating body must be more than symbolic, because technical disputes can be political weapons. If one faction claims the carbon scrubbers are failing, and another claims the claim is propaganda, the court needs access to censors, it needs expert panels, and it needs a process for dissenting technical opinions. Otherwise, engineering becomes theology, and theology is hard to debug. A court that can read sensor logs must also understand how sensors lie. Instruments drift, calibration gases expire, and software filters can smooth away early warnings. A competent judiciary therefore needs technical staff, and those staff need independence. Otherwise, the truth becomes whatever the operations director prints. In a ship, epistemology is governance, because knowing is the first act of control. Transparency is the next hard requirement, because secrecy breeds conspiracy faster than it breeds stability. The ship must publish the state of air, water, power, and reserves in understandable terms. It must also publish the assumptions behind forecasts, because forecasts become arguments. When people cannot see the model, they assume the model is a lie. In practice, transparency is a visual language as much as a legal one. Imagine a public systems board in the main concourse. Air composition, CO2 partial pressure, water recycling efficiency, nutrient stock, battery reserves. Each number has a green band, a yellow band, and a red band that everyone learns as a child. The board updates like a heartbeat, and the ship's mood updates with it. The board is not only numbers because numbers alone can feel like judgment. It shows trends, not just snapshots. Arrows, slopes, and time to threshold estimates that make risk legible. It also shows what is being done, because action reduces panic more reliably than reassurance. In the reflected light, faces pause, calculate, and then continue walking. Yet transparency has a cost, because fear is also contagious. Raw data without context can trigger panic, hoarding, and scapegoating, especially when people do not understand lag and uncertainty. A temporary dip in oxygen production might be a sensor calibration issue, but rumours do not wait for calibration. The ship must build literacy alongside openness, so numbers do not become weapons. Education becomes governance, because informed citizens are harder to manipulate. Statistical literacy matters, because the ship lives on margins and confidence intervals. People must understand that a forecast is not a promise, and that error bars are honesty, not weakness. When leaders hide uncertainty, they buy short-term calm and long-term betrayal. On Earth, public health learned this lesson in outbreaks and disasters, when mixed messages turned caution into suspicion. A generation ship cannot afford that cycle, because trust is not a luxury reserve. Once trust collapses, every announcement becomes a negotiation, and negotiations consume time that emergencies do not grant. The ship must teach uncertainty as a normal part of reality, like gravity, like wear. The danger is that governance becomes theatre while systems drift. Leaders can perform competence, while maintenance debt accumulates behind panels and inside ducts. On a ship, maintenance debt is not a metaphor, it is corrosion, biofilm, and micro cracks. A ship needs institutions that reward boring truth over inspiring narrative. It needs career paths where whistleblowing is protected, not punished. It needs inspectors who cannot be fired by the people they inspect. It needs a culture where a technician can say, "This pump is failing," and not be accused of disloyalty. In a sealed world, loyalty to truth is loyalty to air. Now move from constitutions to the daily politics of scarcity. In a closed habitat, resources are not commodities from outside. They are shared internal organs, and every allocation decision touches survival. Rationing is inevitable, because buffers are finite and shocks are guaranteed. Even with advanced recycling, nothing is perfectly closed. Water loops lose molecules through leaks, sampling and waste that cannot be fully recovered. Air loops lose efficiency as sorbents age and seals creep under thermal cycling. Food loops depend on nutrients that must be conserved, sterilised and returned without poisoning the soil. The ship is a loop with friction, and politics is how friction gets paid. That friction has a chemistry, and chemistry has a timeline. Activated carbon saturates, ion exchange resins foul, and membranes slowly clog with organics that no filter catches forever. Even metals migrate. Trace copper, zinc and nickel leach into water, then must be captured before they become toxic. The ship's economy is therefore a metabolism, and every policy is a diet. Rationing can be equal, yet equality can still feel unjust if needs differ. A technician in a hot maintenance zone may need more water than an office worker. A pregnant person may need more calories than a healthy adult. A child may need micronutrients that adults can tolerate losing for a while. The ship must define fairness as a measurable policy, not a slogan. It must decide whether fairness means equal shares, equal outcomes, or equal risk. It must decide which variables matter: age, workload, medical status, exposure to radiation, or caregiving. Each choice becomes a precedent, and precedents become identity. Those variables must be verified, which creates its own politics of measurement. If workload determines calories, then who certifies workload and who audits the certifiers? If medical status determines rations, then privacy collides with survival accounting. The ship learns an old truth in a new setting. Bureaucracy is not paperwork, it is power. Inequality is not only moral tension, it is a system's risk. If some groups consistently receive better food, better air, or better medical access, resentment becomes structural. Resentment drives non-compliance, and non-compliance breaks loops. The ship can survive a bad harvest, yet it may not survive a legitimacy collapse. In a closed habitat, non-compliance is not just refusal. It can be quiet, like skipping a sanitation protocol because it feels pointless. It can be subtle, like delaying a maintenance report to avoid blame. It can be contagious, like a culture of everyone does it spreading through families. The ship's stability depends on millions of small obediences. Black markets appear when official channels feel arbitrary or humiliating. They begin with small trades, then expand into hidden inventories and hidden power. In a sealed world, black markets are not just economic, they are alternative governance, with their own enforcement and secrecy. A black market can start with extra vitamins traded for repair favours because someone's child is sick. It can grow into a network that controls access to spare parts because spare parts are leverage. It can become a shadow logistics system that knows more than the official one. When the shadow system is more reliable, legitimacy migrates. The externalities are brutal because small acts can cascade into life support failure. Stealing a filter cartridge is not theft. It is a future CO2 spike. Diverting water is not a private choice. It is a microbial risk for everyone. The ship must teach externalities as civic reality, because physics enforces them without appeal. Closed-loop ecology makes this sharper, because the ship's environment is engineered and alive. Microbes in the water system form biofilms that can resist disinfectants, and nutrient imbalances can invite blooms that clog lines. A single contaminated reservoir can spread illness through shared plumbing. In a habitat with shared air, violence can be chemical, not visible. Even well-meaning shortcuts can become ecological sabotage, because ecosystems respond to incentives, not intentions. If someone dumps nutrient concentrate to help the plants, the runoff can feed algae in a greywater tank. If someone bypasses a sterilization cycle to save time, resistant strains can be selected and then entrenched. The ship's biology is always listening, and it learns quickly. Sabotage is the darkest form of resource conflict, and it is uniquely catastrophic here. A cut cable can disable pumps, and a disabled pump can kill crops. A contaminated tank can spread illness through shared plumbing. A misconfigured control algorithm can drive a system into oscillation, and oscillation can become collapse. This is why governance must treat infrastructure as sacred, even without religion. Certain systems must be protected by design, with compartmentalization and access control. Critical valves and software must require multiple authorizations, because single-person control is a temptation. The ship must assume that conflict will occur, then design so conflict cannot easily become mass death. Compartmentalization is not only physical, though physical bulkheads matter. It is also informational. Who can change code? Who can update firmware? Who can override alarms? Audit logs must be tamper-resistant, and oversight must be routine rather than reactive. A society that only inspects after disaster is a society that has already chosen disaster. Education is the next fragile institution, and it functions like oxygen. The ship cannot rely on stored manuals alone, because knowledge decays without practice. A library can preserve words, yet it cannot preserve competence. Competence lives in habits, muscle memory, and the ability to diagnose unfamiliar failures. On Earth, industries learn this through hard lessons. Nuclear plants, aircraft maintenance, and hospital systems all discovered that procedures drift when they are not rehearsed. People simplify steps, skip checks, and normalize small deviations until the deviation becomes the norm. In a generation ship, normalization of deviance is not a management problem, it is a mortality curve. Technical education must therefore be continuous and structured across generations. Apprenticeship cultures become essential because they transmit tacit knowledge that documents miss. Every critical system needs a pipeline of trainees who have touched the hardware. The ship must avoid single points of expertise because experts die. Imagine a training bay that looks like a small factory, but it is really a school. Mock panels replicate the life support racks, and simulated faults appear without warning. Apprentices learn to listen for the wrong vibration, to smell overheating insulation, to recognize a pump that is cavitating. Elders annotate institutional memory records as they watch, because teaching is also logging. The training bay also teaches calm, because panic is a technical failure mode. Students practice lockout procedures, contamination protocols, and communications discipline until it becomes reflex. They learn that the first step is often to stop, verify, and breathe, because a rushed fix can create a second emergency. In the background, simulation clocks tick like a metronome of consequence. Credential systems must be trusted, because fake competence is lethal. Exams must test real performance, not rote recall. Certification must be renewed, because drift is inevitable in long stability. The ship must treat training time as a protected resource, even when labour is scarce. This requires political courage, because training looks like idleness to the impatient. During shortages, a faction will argue that every person must produce food or repair hull. Yet without training, the next failure becomes unfixable, and the ship trades present output for future collapse. The politics of training is the politics of patience. Institutional memory must be built as infrastructure, not as nostalgia. Maintenance logs must be standardized, redundant, and readable across software changes. Simulation environments must exist, because some failures cannot be practiced on live systems. The ship must preserve not only what happened, but why decisions were made. The why matters because future engineers inherit constraints they did not choose. A design compromise might have been made to save mass at launch, or to avoid a known failure mode. If that context is lost, a well-meaning upgrade can reopen an old wound. Institutional memory is a map of invisible landmines. Language drift is a quiet threat to technical continuity. Terms shift, abbreviations mutate, and old warnings become ambiguous. The ship needs controlled vocabularies for critical systems and translation layers for old records. Otherwise, the past becomes a foreign country inside the same hull. Even pronunciation can matter because spoken commands are part of operations. If a valve name sounds like another valve name, confusion becomes an accident. The ship may need standardized callouts, like aviation did on Earth, because clarity is a safety system. Culture shapes language, and language shapes response time. Now, mental health, because society is also a psychological ecosystem. Confinement is not a temporary mission stress, it is a lifelong condition. Monotony erodes attention, and attention is what keeps life support stable. Intergenerational trauma can accumulate because children inherit the anxieties of parents. The ship's environment is stable by design, yet humans are not built for perfect sameness. Circadian rhythms still crave sunrise and sunset, even if the ship provides artificial cycles. The brain still seeks horizons, even if the corridors curve and repeat. When novelty disappears, people manufacture it, sometimes through conflict. A ship must design for novelty without wasting resources. Rotating habitats, changing schedules, and reconfigurable public spaces can create perceived variety. Lighting can shift seasonally, and soundscapes can mimic weather that does not exist. Even small changes, new murals, new music, new festivals, can reset attention. Visually, these changes matter because they give the eye a future. A corridor that once looked identical for a kilometre becomes a sequence of neighbourhoods, each with colour, temperature and texture. A garden dome shifts from bright summer whites to amber autumn tones, and people feel time again. The ship cannot offer wilderness, but it can offer rhythm. Art and play are not indulgences because they regulate stress and reduce conflict. They provide safe status competitions that do not involve hoarding or sabotage. They allow grief to be expressed without turning into violence. In a closed world, emotional ventilation matters as much as air ventilation. Ritual can stabilize identity, because identity reduces the need for destructive status contests. A maintenance rite that honors the people who keep the ship alive can turn invisible labor into visible pride. A coming-of-age ceremony tied to civic responsibility can make rationing feel like membership rather than punishment. Ritual is a social algorithm that runs on emotion. Purpose is the strongest psychological buffer, yet it is also fragile. The opening hook returns in a different form because rescue is not coming. If the universe offers no shortcuts, then meaning must do what rescue cannot. People must believe that their maintenance labor matters, even when the destination is a star no one has seen. Narrative becomes a control system. A shared story can keep people aligned with long-term constraints that feel unfair in the short term. Yet stories can also fracture, because different groups interpret sacrifice differently. When stress rises, factions form around competing explanations. One story says the ship is a covenant with the future, and every generation pays a fair share. Another story says the ship is a prison built by ancestors, and obedience is exploitation. Another story says the ship is a test, and suffering proves virtue. Each story produces different politics, even if the air is the same. Religions and myths are not optional in a multi-generational habitat. They emerge because humans seek patterns, and the ship is a total environment. The ship itself can become sacred because it is the source of air and water. Maintenance can become liturgy because it repeats and it saves. Visually, sacredness can be subtle. A worn handprint on a hatch becomes a talisman because thousands touched it before entering the garden. A quiet alcove near the water plant becomes a shrine because water is life and life is scarce. The hum of the reactors becomes a chant that no one remembers learning. Sacralizing the ship can protect infrastructure, yet it can also block necessary change. If a subsystem becomes holy, then redesign becomes heresy. A taboo against touching certain spaces can prevent repairs. The ship must manage sacredness carefully because it can stabilize or fossilize. This management is delicate because suppressing belief can backfire. On Earth, attempts to erase religion often created stronger underground movements. In a ship, underground movements are dangerous because they hide. The goal is not to eliminate myth, but to align myth with survivable behavior. Mission drift is the political version of orbital drift. Over centuries, the destination can become abstract, then symbolic, then contested. Some may become arrival denialists, arguing the star is a myth used to justify control. Others may become returnists, arguing the ship should turn back, even if turning back is impossible. Arrival denialism can be fed by the ship's own success. If life is stable enough, the destination feels less urgent, and urgency is what keeps the mission coherent. People may ask why they should endure rationing for a place they will never see. They may ask whether the star is real, or whether it is a story to keep them compliant. Returnism can be fed by grief and nostalgia, even when Earth is only an image. Archives show blue skies, oceans, and forests that seem like miracles compared to metal corridors. A faction may argue that the ship is a mistake, and that the moral act is to undo it. The tragedy is that physics may not allow undoing. These factions are not irrational in their own terms. They are responses to the same psychological problem, which is living for a future you will not see. If the mission is framed as debt to ancestors, some will reject the debt. If it is framed as salvation, some will demand purity and obedience. Pluralism becomes a survival requirement because forced uniformity produces underground resistance. Yet pluralism must have boundaries because some beliefs can justify sabotage. The ship needs a civic compact that protects private meaning while protecting shared infrastructure. It must define non-negotiables in operational terms, not theological terms. The non-negotiables are simple, even if the politics is not. Do not damage life support. Do not hide contamination. Do not falsify logs. Do not hoard critical spares. These are not moral preferences but physical constraints. Violating them is like violating gravity. Conflict resolution is the next institution that must endure. On Earth, conflict can be displaced by distance or cooled by time and new opportunities. On a ship, conflict recirculates like air, and grudges can become family inheritance. The ship needs systems that resolve disputes before they become security problems. Restorative justice is attractive because it preserves cohesion and reduces cycles of revenge. It treats harm as damage to relationships, which is accurate in a closed habitat. It also requires trust and participation, which may fail during crisis. When fear rises, people prefer punishment that feels immediate. Coercive justice is faster, yet it risks creating martyrs and permanent opposition. A harsh sentence can turn a petty thief into a symbol, and symbols recruit. In a sealed world, recruitment is dangerous because it concentrates resentment. The ship must be careful not to manufacture enemies by overreacting. The ship likely needs both, with clear thresholds and oversight. Minor violations can be handled through restitution, mediation, and monitored reintegration. Major threats to life support require containment because the externalities are too large. The key is that punishment must be predictable, because arbitrary punishment is a recruitment tool for factions. Containment itself raises hard questions, because the ship cannot exile people. A prison module consumes air, food, and supervision, and it can become a school for extremism. Yet some individuals may be too dangerous to leave unrestrained. The ship must decide what humane containment looks like when space is a precious commodity. Even the architecture of containment becomes a moral signal. If it is brutal, it teaches that power is brutal, and brutality spreads. If it is too lenient, it teaches that sabotage is survivable, and temptation grows. The ship must balance deterrence with reintegration, because every person is also a unit of labor. Security itself must be redesigned for a habitat where gunfire is catastrophic. Bullets can puncture pressure walls, damage coolant lines, or ignite fires in oxygen-rich zones. Non-lethal control becomes the default, using barriers, restraints, and disabling technologies. The ship must train security as de-escalators first, because escalation can kill everyone. Security tools must also respect the ship's materials and atmosphere. Chemical irritants can contaminate filters and harm asthmatics. Electrical weapons can interfere with sensitive control electronics. Even a stampede can overload a floor section or block an evacuation corridor. Security doctrine becomes a branch of safety engineering. Surveillance is tempting because it promises early detection of sabotage and conspiracy. It also corrodes privacy, which corrodes trust, which then increases conspiracy. The ship must decide what it monitors, who can access records, and how abuse is punished. A surveillance system without accountability becomes a coup machine. Accountability needs more than rules, because rules can be rewritten. It needs technical constraints, immutable logs, multi-party access, and independent audits. It needs visible consequences for misuse, even when the misuse is politically convenient. Otherwise, surveillance becomes a silent constitution that overrides the written one. Emergency powers are the most dangerous clause in any charter. Real emergencies will occur, from radiation storms to crop failures to epidemics. In those moments, centralized command can save lives by acting quickly. The risk is that emergency becomes a permanent justification, because fear is politically useful. A durable system defines emergencies in measurable triggers, tied to life support margins and verified by independent sensors. It defines time limits, renewal procedures, and post-crisis audits. It defines what cannot be suspended, including basic rights and oversight. Without these limits, the ship trades short-term order for long-term legitimacy collapse. The measurable triggers must be legible to ordinary citizens. If only experts can interpret them, then experts become kings by default. The ship must translate technical thresholds into civic language, so people can consent intelligently. Consent without understanding is not consent, it is compliance. Leadership selection is another slow fuse. Elections can renew legitimacy, yet they can also become popularity contests that reward comforting lies. Appointments can preserve competence, yet they can also entrench a class. A hybrid model may be necessary, where technical roles require certification and civic roles require consent. Even then, the ship must guard against charismatic capture. A leader who promises abundance can gain power by denying constraints. A leader who promises purity can gain power by inventing enemies. In a sealed world, enemies are always inside, which makes scapegoating dangerously convenient. Charisma can also attach to expertise, which is its own hazard. A brilliant engineer may become a political oracle, and dissent may be framed as ignorance. Yet experts can be wrong, and systems can surprise even their designers. The ship needs a way to respect expertise without worshipping it. The antidote is institutional humility, built into routines. Regular public briefings must include uncertainty and error bars, not only confidence. Independent review boards must exist, with authority to inspect and publish. The ship must normalize dissent as a diagnostic tool, because suppressed dissent becomes sabotage. Dissent must also be trained because not all dissent is useful. People need to know how to argue from evidence, how to separate values from facts, and how to propose alternatives. Otherwise, debate becomes performance, and performance becomes factional identity. The ship cannot afford debates that generate heat without light. Culture can either support that humility or destroy it. If the ship values obedience over understanding, then errors will be hidden. If it values understanding over status, then errors can be corrected early. The ship's survival depends on which virtues it rewards in childhood, so education returns, now as civic education. Children must learn systems thinking, because the ship is a system. They must learn why rationing exists, why quarantine exists, and why redundancy is not waste. They must also learn how to argue without breaking the social fabric. Systems thinking can be taught with tangible metaphors. A classroom model of the water loop shows how contamination spreads and how purification has limits. A simple simulation shows how small hoarding events amplify into shortages. When children see feedback loops, they grow into adults who respect them. A society that cannot argue safely will eventually fight unsafely. The ship must provide legitimate channels for grievance, because grievances will exist. It must also provide ways to change policy without revolution, because conditions will change. Revolution in a sealed habitat is not romantic, it is a risk to oxygen. Legitimate channels must feel real, not ceremonial. Petitions must lead to hearings, and hearings must sometimes change outcomes. Investigations must sometimes punish powerful people, or the system teaches cynicism. Cynicism is corrosive because it makes sabotage feel justified. Over centuries, the ship's meaning will be renegotiated repeatedly. Some generations will feel chosen, others will feel trapped. Some will treat the mission as inheritance, others as imprisonment. Governance must survive these mood swings without relying on constant enthusiasm. This is the political version of closed-loop engineering. Institutions must recycle trust the way life support recycles water. They must filter toxins like corruption and secrecy, and they must replenish legitimacy through fairness and competence. If they fail, the ship becomes a pressure vessel full of factions. The central question now has a sharper edge. Could a generation ship sustain a stable human population and functioning ecosystem for centuries? Or will the most fragile subsystem be the one made of beliefs, incentives, and power? The unsettling observation is that politics is not separate from engineering. Politics decides who gets trained, who gets listened to, and which warnings become action. Politics decides whether the ship invests in redundancy or spends it on comfort. Politics decides whether truth is rewarded or whether truth is punished as disloyalty. Even if governance holds, society still lives inside physics. A stable charter cannot stop radiation from accumulating, and a fair court cannot reverse material fatigue. The next chapter turns outward again, toward hazards that do not negotiate. Radiation storms, dust impacts, hardware aging, and the quiet cosmological risks that build until they break. A generation ship's lifespan is not decided by a single technological miracle, but by the long, quiet negotiation between physics, biology, and human nature, proving that the hardest part of crossing the stars may be learning to keep a world alive when it is all you have. Chapter 5 ended with a hard truth. Even perfect governance still lives inside physics. Deep space looks empty from a window, especially when the stars feel pinned to a black motionless dome. In practice, it is a thin, fast, abrasive environment that never stops. An ocean of particles so sparse you could call it vacuum, yet so relentless, it becomes weather. The central question tightens again. Could a self-contained generation ship survive centuries when every year adds damage that cannot be fully undone, and when every repair consumes time, mass, and attention? Start with the interstellar medium, because it is the background hazard that never takes a day off. Between stars, gas densities are low, yet the ship's velocity turns rarity into impact, and impact into a slow accounting of surface loss. A few atoms per cubic centimetre sounds like nothing, a number too small to fear. At tens to hundreds of kilometres per second, each atom becomes a tiny projectile that deposits energy, knocks atoms out of lattices, and erodes surfaces one collision at a time. This is not the atmosphere's drag, and it is not the gentle pressure of sunlight. It is a collision problem, governed by relative velocity and cross-section, where even a single hydrogen atom can arrive with enough kinetic energy to damage a thin film. Dust is worse than gas, because it carries mass and momentum in concentrated form. A grain smaller than sand can strike with rifle-level energy at high relative speed, depending on velocity, composition, and whether it is porous or dense. In the lab, hypervelocity impacts behave strangely, almost like fluid dynamics in solid materials. Metals jet, ceramics shatter into conical sprays, and composites delaminate. So the ship's skin is not simply punctured, it is transformed locally. The ship is not hit once, and it is not hit in a dramatic burst. It is hit continuously by a sparse rain that becomes sandblasting over decades, until the outermost layers look frosted, pitted, and tired under harsh light. Engineers quantify this as flux and risk, because intuition fails at century scales. How many particles per square metre per year, at what size distribution, at what velocity, and with what shielding response? Those parameters become as political as they are technical. The distribution matters more than the average, and that is the trap. Many tiny impacts create erosion and pitting, while rare larger grains create punctures and spool that propagate cracks, turning a single strike into a long-term weakness. There is also directionality, because the ship has a forward face. Over time, the bow becomes the sacrificial shoreline, while the wake remains comparatively calm, and that asymmetry shapes everything from radiator placement to docking geometry. The first design response is geometry, because geometry is free until it isn't. Present less area, avoid fragile protrusions, and align critical surfaces behind sacrificial layers, so that the ship's vital organs sit in the shadow of expendable skin. That choice changes the visuals of the vessel in flight. Instead of a delicate cathedral of antennas and trusses, the ship becomes a blunt, layered form, more like a deep-sea submersible than a sleek aircraft. The second response is shielding, and the classic tool is the Whipple shield. A thin bumper layer sits ahead of the pressure hull, separated by a standoff gap, and the gap is as important as the metal. When a particle hits the bumper, it vaporizes and fragments, and the physics happens in microseconds. The debris cloud spreads, and the main wall sees a wider, lower energy spray like a shotgun pattern instead of a single bullet. Whipple shielding is not magic, and it is not a guarantee against the largest grains. It trades a single hole for distributed damage, and it still requires enough thickness to stop the debris, which means the mass bill never disappears. Designers also worry about what the shield becomes after decades of hits. A bumper riddled with craters changes its own behaviour, and a standoff gap can fill with fragments, turning a clean design into a messy, evolving structure. Standoff distance becomes a design variable and a constant compromise. More distance improves dispersion, yet it increases structure mass and complicates internal layout, because empty space is never truly empty once you must support it. Sacrificial layers extend the idea, and they make the ship feel like a living organism. Outer skins are designed to be replaced, resurfaced, or gradually ablated without exposing the pressure vessel, and the ship's exterior becomes a consumable resource. That replacement is a maintenance promise, not a slogan. It requires access, tooling, and safe work practices in vacuum over centuries, and it requires a culture that treats routine exterior work as normal rather than heroic. Every external repair also becomes a radiation and micrometeoroid exposure event. The ship must schedule it, shield it, and record it, because the environment does not pause for a shift change or a holiday. Mass is the constant antagonist, because it sits behind every good idea. Every kilogram of shielding is a kilogram not used for habitat volume, water buffer, manufacturing stock, or redundancy, and the trade is never settled once. A ship can be heavily armoured and still fail if it cannot break at arrival. A ship can be lightly armoured and still fail if it accumulates unrepaired punctures, and the difference between them is not bravery, but bookkeeping. So the design becomes a risk budget, with numbers that must be defended. Accept a certain rate of impacts, then build inspection and repair systems that can keep up, and make sure those systems can be maintained by the people they protect. Inspection is harder than it sounds because damage hides in the seams of material science. Microcracks and delamination can hide under coatings, and sensors drift over time until the ship's skin becomes a landscape of unknowns. The ship needs a layered detection strategy, because no single sensor sees everything. Acoustic emission monitoring, pressure decay tests, distributed fiber sensors, and periodic robotic scans. Each one catches a different failure mode. Fiber optic strain sensing can turn a hull into a nervous system, yet even that nervous system ages. Adhesives creep, calibration shifts, and the meaning of a signal changes as the structure slowly evolves under stress. Robots help, and they change the visual language of maintenance. Small crawlers grip the hull like insects, while larger arms move deliberately along rails. Yet robots also age, and they fail in ways that are easy to underestimate. Actuators wear, lubricants outgas, and radiation flips bits in control electronics. A robot that fails outside is not just broken equipment, it is debris, a hazard, and a reminder that autonomy is never absolute. A key insight emerges here, and it is almost philosophical. The ship must be designed for maintainability first, because the environment guarantees a steady stream of small failures, and the future is shaped by how gracefully you handle the small ones. Now, radiation, because it is the patient predator that reaches everywhere. It attacks DNA, electronics, and materials at the same time, and it does so invisibly, without sound, without heat, and without a clear moment of impact. Radiation comes in regimes, and the ship moves through them like climate zones. Near departure and arrival, the ship is exposed to solar particle events, and in deep interstellar cruise, it is dominated by galactic cosmic rays. Solar particle events are bursts of protons and heavier ions, often tied to flares and coronal mass ejections. They can raise dose rates dramatically in hours, and they can exceed shielding assumptions if the storm is extreme. Historically, Earth has been protected by a magnetic field and an atmosphere, and even then solar storms have left fingerprints. The Carrington event of 1859 lit telegraph wires on fire, and it hints at what an unshielded spacecraft would face. Galactic cosmic rays are different, and in some ways more unsettling. They are high-energy nuclei, often relativistic, arriving from supernova remnants and other violent accelerators, carrying energies that make shielding feel thin. They are hard to stop because they do not politely slow down in a few centimeters of metal. Thick shielding can reduce dose, yet it can also create secondary particles when cosmic rays strike heavy atoms, and those secondaries spread the harm. This is why hydrogen-rich shielding is favoured, because it reduces secondary neutron production. Water, polyethylene, and food mass become part of the radiation architecture, turning the ship's pantry into a defensive wall. This creates a design coupling that earlier chapters hinted at, and it tightens here. Water is life support, thermal mass, and radiation shielding, all in one ledger, which means waste and storage become geometry. The ship's layout becomes a dose map, and the map becomes a moral document. Sleeping quarters, nurseries, and clinics are placed near the most shielding mass, while workshops and exterior access points accept higher exposure as a cost of function. The storm shelter is the simplest operational answer, and it is also the most human. During solar events, people move into a compact core wrapped in water tanks, food stores, and waste processing mass, and the ship briefly becomes a bunker. Visually, the shelter is not dramatic, and that is the point. It is a tight corridor of soft light, stacked containers, and quiet airflow, an interior within an interior, designed to make fear manageable. This is not only a shelter, and it is not only a technical feature, it is a drill, a ritual, and a test of governance under fear, because the alarm forces everyone to remember that the universe can still reach them. Storm shelters must be sized for the whole population, or the ship must decide who fits. That decision is political, and it must be settled before the first alarm because a crisis is the worst time to invent ethics. Dose management becomes a lifetime accounting problem, not a single threshold. Even low daily doses accumulate into cancer risk, cataracts, cardiovascular damage, and fertility impacts, and the statistics become personal over generations. The ship must set exposure limits, then enforce them through work scheduling and habitat zoning. Maintenance crews doing external repairs take higher doses, and that risk must be rotated fairly, with transparent records that cannot be quietly edited. Radiation also interacts with genetics, and the ship cannot pretend otherwise. Higher mutation rates in germ cells add to drift and inbreeding pressures described earlier, and the difference between manageable and catastrophic may be a few percentage points. The cryobank returns as both hope and vulnerability, and it carries a strange symbolism. If radiation or power failures degrade stored samples, the ship loses its external continent of diversity, and the future narrows without anyone noticing at first. Cryogenic storage needs stable power, stable containers, and stable records all at once. A century-scale mission turns every label into a language preservation problem, because a vial is useless if its meaning becomes ambiguous. Now, cosmic weather in a broader sense, because the ship leaves one star's heliosphere and travels through changing interstellar fields. The magnetic environment shifts, the plasma density shifts, and the background radiation can rise or fall in ways that are measurable but not fully predictable. Magnetic field variations modulate particle flux, and the ship must watch the sky like sailors watched clouds. The ship cannot predict every fluctuation, so it must build margins and monitoring, and it must treat surprise as normal. Active shielding is often proposed, using magnetic or electrostatic fields, and the idea is seductive. In practice, it adds complexity, quench risks, and power demands that must endure for centuries, and each of those words hides a failure mode. A field strong enough to deflect high-energy ions is not gentle, and it is not passive. It can interfere with electronics, impose structural loads, and create failure modes that are hard to repair, especially if superconducting systems lose stability. So most realistic designs fall back to passive mass and operational shelters because they degrade more gracefully. The ship accepts that some radiation is unavoidable, then manages the long-term consequences, and that acceptance becomes part of the culture. Radiation is not only a biology story, and it is not only a medical chart, it is also an electronic story, because computation is the ship's nervous system, and a nervous system that hallucinates can kill. Single event upsets flip bits in memory and logic, sometimes with no visible trace. Over time, they corrupt data, crash controllers, and create subtle faults that look like human error, which is why blame becomes such a dangerous reflex. Error correction helps, yet it is not free, and it is never perfect. Redundant memory, scrubbing routines, and triple modular redundancy add power draw and hardware mass, and they add diagnostic complexity that must remain understandable. The deeper problem is common mode failure, and it haunts every redundant architecture. A software bug replicated across redundant systems can fail everywhere at once, and a mistaken update can turn a safety net into a synchronized collapse. This chapter's tension builds here, because it is not about one bolt or one storm. Redundancy can still collapse, if the same assumptions are copied into every backup, and if the organization forgets how to challenge its own certainty. Now, material's aging because entropy is not dramatic, and that is why it wins. It is the slow grind that turns margins into debts, and it does so through mechanisms that are measurable yet easy to postpone. Radiation embrittlement changes metals and composites, and the change is microscopic at first. Displacement damage creates defects, and those defects reduce toughness and fatigue life, until a material that once bent begins to crack. Thermal cycling is constant, especially on external structures that see sun and shadow. Radiators, external skins, and rotating structures experience temperature swings that drive expansion and contraction, and every swing is a tiny mechanical argument. Fatigue accumulates from these cycles, and fatigue is a quiet mathematics. Microcracks grow invisibly until they link, and then a part fails without warning, often after it has performed perfectly for years. Creep matters in rotating habitats, because rotation turns time into stress. Hoop stress in the ring or cylinder slowly stretches materials, and long-term deformation changes alignment and bearing loads. making friction and vibration creep upward. Corrosion returns from inside, and it is more intimate than impacts or radiation. A humid biosphere is chemically aggressive, especially where salts, organic acids, and microbes contact metals, and the ship's own life becomes an industrial environment. Even stainless alloys pit in the wrong conditions, and the wrong conditions are easy to create. Crevices become oxygen-starved, biofilms create local chemistry, and corrosion becomes a hidden ecosystem, feeding on neglect. Polymers degrade too, and their failure is often sudden in function even when slow in cause. Radiation breaks chains, plasticizers migrate, seals harden, and flexible parts become brittle, until a gasket that once yielded becomes a crack line. A seal that fails is not a small inconvenience, and it rarely fails at a convenient time. It can be a slow leak, a contamination pathway, or a fire risk, and it can force emergency work in the worst possible conditions. Electronics age under heat and radiation, and they age even when they are idle. Solder joints crack, capacitors dry out, and connectors oxidize in trace contaminants, and the ship's nervous system becomes increasingly sensitive to vibration and temperature. So the ship needs a material strategy that assumes replacement, not immortality. It must choose alloys, composites, and polymers with known aging behavior and repair pathways, and it must keep the ability to test and certify repairs. This pushes against the temptation for exotic optimization, which is always attractive on paper. High-performance materials that cannot be fabricated on board become liabilities after the first century, when supply chains are a memory and improvisation becomes routine. The ship therefore favors robust, repairable, low-complexity systems, even when they look less elegant. It chooses designs that can be understood, diagnosed, and rebuilt with limited tools, because comprehension is a form of redundancy. Complexity is not only parts count, and it is not only wiring diagrams. It is also dependency chains, where one specialized component blocks an entire subsystem, and where a missing connector can immobilize a machine that otherwise works. That leads to the next constraint, and it is defining trade. Spare parts versus self-manufacture becomes a central question, because the ship must decide what it carries finished and what it carries as potential. A ship can launch with a vast inventory, stacked like a warehouse behind the habitat walls. Over centuries, inventory becomes dead mass unless it is managed, rotated, and protected from degradation, and that management itself consumes labor. Some spares expire even when untouched, because chemistry does not care about intention. Lubricants polymerize, elastomers crack, and batteries lose capacity even on a shelf, so the ship must treat storage as an active system. Other spares become obsolete, and obsolescence is a quiet kind of betrayal. Interfaces change, software assumptions drift, and a perfectly preserved board no longer fits the upgraded bus, turning treasure into scrap. So inventory strategy must be dynamic, and it must be documented like a living organism. The ship needs a living catalogue, with usage rates, failure statistics, and planned redesign cycles, so that the future is not surprised by the present. Self-manufacture promises autonomy, and it is hard to resist. If the ship can fabricate parts, it can trade raw stock for flexibility, and it can respond to unknown failures that no launch inventory could anticipate. But manufacturing is itself a complex ecosystem, with its own fragility. It needs feedstock, machine tools, metrology, calibration standards, and skilled operators, and it needs a culture that respects tolerances and process discipline. It also needs quality control, because a bad part is worse than no part. A part that fails early is not only waste, it is a risk multiplier that consumes labor and erodes trust, and mistrust can paralyze maintenance. Mining onboard stockpiles becomes a bridge strategy, and it is visually straightforward. The ship carries bulk metals, ceramics precursors, and polymer feedstocks as generic reserves, stored like geological strata in the ship's deeper compartments. Recycling becomes non-negotiable, and it becomes a daily habit rather than a campaign. Near 100% efficiency is not an ideal, it is a practical necessity when resupply is impossible, and when losses compound across centuries. This is where earlier closed-loop themes return with steel and silicon, not just water and air. Every atom that leaves the loop is a countdown, and the ship must learn to see trash as delayed failure. Recycling must handle mixed materials, and mixed materials are the enemy of easy recovery. Composites, adhesives, and electronic assemblies are hard to separate, and separation is where energy and labor vanish. so designs must anticipate their own end of life. Design for disassembly becomes a survival principle, and it shapes aesthetics as well as engineering. Fasteners replace permanent bonds, standardized modules replace bespoke assemblies, and documentation becomes part of hardware, stored redundantly and taught deliberately. The ship must also recycle rare elements, because modern systems depend on them. Copper, nickel, cobalt, and semiconductor dopants cannot be casually lost without future system collapse, and the ship must track them like a central bank tracks currency. Even if recycling works, it consumes time, and time is the ship's hidden currency. Maintenance labour competes with farming, education, and governance, and the competition becomes sharper when a generation grows comfortable. Maintenance debt is the silent killer, because it feels rational in the moment. When a generation postpones repairs to improve comfort, it hands the next generation a thinner margin, and the next generation inherits both the damage and the story. Now catastrophic scenarios, because the interstellar environment does not only erode, it occasionally strikes hard, and the ship must be prepared for events that are rare yet decisive, the way earthquakes shape cities. A hull breach is the iconic fear, and it deserves its reputation. Yet most breaches begin small, and that is what makes them dangerous, because small failures invite denial until they become emergencies. A puncture becomes a leak becomes structural stress, and stress becomes a tear. The ship's internal pressure is always trying to escape, and a flaw gives it a direction, turning a pinhole into a long argument with physics. Compartmentalization is the primary defense, and it is as much architecture as it is procedure. The ship is divided into pressure zones with automatic isolation, so one failure does not become total loss, and so evacuation routes remain meaningful. Isolation requires sensors that can be trusted, and trust must be earned repeatedly. False positives can trap people, while false negatives can kill them, so the ship must calibrate not only instruments, but also the culture that responds to alarms. Emergency protocols must be rehearsed until they are reflex, because cognition narrows under stress. In a crisis, confusion is as dangerous as vacuum, and the ship cannot afford to discover its own bottlenecks during an actual event. Fire is another existential threat, and it is historically one of spaceflight's darkest lessons. In oxygen-rich environments, materials ignite easily, and smoke contaminates filters that the ship cannot replace casually, turning a local flame into a system-wide hazard. Fire suppression must avoid secondary harm, and every method has a cost. Water damages electronics, powders foul machinery, and inert gases can asphyxiate in sealed compartments, so the ship needs suppression tailored to each space. So the ship needs layered fire strategy, and layered means redundant in different ways. Low flammability materials, strict ignition control, distributed detection, and compartment-specific suppression, with clear training that survives changes in language and custom. Runaway contamination is less cinematic and more likely, and that is why it belongs beside fire. A pathogen bloom in water systems, a toxin in a bioreactor, or a mold in ventilation can spread through shared loops, and the ship's connectivity becomes its weakness. Containment again becomes architecture, and architecture becomes policy. Separate air handling, quarantine modules, and the ability to reroute flows without shutting down the whole habitat, because the ship must isolate problems without suffocating itself. Reactor failure is the hardest scenario to narrate honestly, because it touches every other subsystem. Power is life support, and long-duration power systems have their own aging curves, their own maintenance rituals, and their own political sensitivities. A nuclear reactor offers high energy density, yet it brings radiation fields, coolant risks, and long-term materials damage in the core. Over decades, neutron flux changes alloys, seals, and instrumentation, and the reactor becomes a managed aging process. A fusion system promises cleaner operation, yet it demands extreme complexity and high-performance components that may not be manufacturable on board. If it fails in a way that requires Earth-level industry, then it is not autonomy, it is deferred dependence. Whatever the power source, the ship must plan for partial loss, because perfection is not a plan. It needs load-shedding priorities that keep air, water, and heat rejection alive, even if lighting dims and comfort systems go silent. Redundancy helps, yet common mode errors return, and they return with teeth. A design flaw, a procedural drift, or a contaminated batch of replacement parts can defeat multiple backups, and the ship must be honest about how often humans repeat mistakes. This is why risk management is a discipline, not a checklist, and not a binder on a shelf. The ship must continuously update failure models with real data from its own aging hardware, and it must treat anomalies as gifts rather than embarrassments. It must also preserve the culture of reporting, even when reporting is inconvenient. If technicians hide near misses to avoid blame, the ship loses its early warning system, and small failures regain the power to become catastrophes. Now, navigation, because survival is not only staying alive, and not only staying stable, it is arriving with the ability to do something once you get there, and arrival is a technical act that cannot be improvised at the end. After centuries, small errors accumulate, and they accumulate quietly. Star trackers drift, inertial sensors bias, and ephemerides become historical documents that must stay interpretable, even as calendars, units, and assumptions evolve. Navigation is a chain of measurements and models, and the chain is only as strong as its weakest link. If any link degrades, the ship can miss its target by astronomical distances, and the tragedy is that the miss may be invisible until it is too late. Course corrections require propellant or reaction mass, and reaction mass is finite. Every correction is a trade against braking and maneuvering later, and the ship must decide how much uncertainty it can afford to carry forward. Arrival risk is therefore a compound problem, not a single burn. The ship must hit a narrow corridor in space and time, then decelerate without margin collapse, while its systems are older than any machine in human history. Deceleration is the final test of earlier constraints, and it is unforgiving. High velocity shortens travel time, yet it increases shielding needs and makes braking energy enormous, so the ship's schedule is written in mass and heat. If the ship uses propulsive braking, it needs fuel stored and protected for centuries, and storage is never neutral. Tanks leak, seals age, cryogens boil off, and even stable propellants can become contaminated by slow chemical change. If it uses sails or magnetic braking, it needs large structures that must survive impacts, and that survival is not guaranteed. A sail that tears, or a magnetic loop that fails, can turn a controlled arrival into a flyby measured in minutes. A crippled ship at arrival is a special kind of tragedy, because it is so close to meaning. It can reach the destination star and still be unable to brake, orbit, or land, and the new sun becomes a spotlight on failure. It can also arrive with a damaged biosphere, and that damage can be subtle at first. A stressed ecology may survive cruise, then collapse under the additional demands of arrival operations, when power and attention are pulled toward navigation and braking. The arrival bottleneck from Chapter 4 returns in a harsher form, and it does not negotiate. A weakened immune system meets a new biosphere, while the ship is busy braking and repairing, and the margin for medical surprises is thin. So the ship must arrive with reserves, and reserves must be real, not rhetorical. Reserves of power, reserves of reaction mass, reserves of spare parts, and reserves of human attention, because attention is the only resource that can reallocate everything else. Attention is the scarce resource that no inventory can replace, and it degrades under monotony. A tired society makes mistakes, and mistakes are amplified by tight margins, especially when the ship's systems have become unfamiliar through gradual change. This chapter's climax is not a single disaster, and it is not a heroic fix. It is the realization that deep space is a long audit of every assumption, and that the audit is performed by physics with perfect patience. The ship can survive micrometeoroids if it can inspect and repair forever, and if it can keep the tools calibrated. It can survive radiation if it can manage dose and preserve genetics, and if it can keep records meaningful across centuries. It can survive materials aging if it can manufacture, recycle, and maintain skills across generations, and if it can keep pride from replacing evidence. But each survival strategy adds mass, complexity, and governance burden, and the ship becomes a balancing act where every solution creates a new failure mode. That is the slow grind of entropy, and it is the chapter's true antagonist. Not a villain that attacks once, but a constant tax on structure, knowledge, and trust, collected quietly in corrosion pits and flipped bits. So the central question returns with maximum pressure, and it is no longer abstract. Could a self-contained generation ship sustain a stable human population and functioning ecosystem for hundreds of years? And what sets the ceiling when the environment never stops charging interest? The ceiling is not a single number, and it is not the same for every design. It is the point where maintenance debt outruns repair capacity, where risk budgets are spent faster than they can be replenished, and where the ship's culture can no longer keep complexity legible. Design philosophy becomes the deciding factor, because philosophy shapes every trade. Favour simplicity, modularity and repairability, even when performance looks lower on launch day, and even when the temptation to optimise feels like progress. Favour buffers that can be measured and defended politically, because invisible buffers are easy to steal. Favour systems that fail gradually, with warning rather than suddenly, and make sure warnings are understood by people who did not build the original machine. Favour diversity in tools and methods, so one flawed assumption does not kill every backup. Then admit the final constraint, because honesty is part of survival. Even the best design cannot eliminate chance. It can only negotiate with it. After biology and society and entropy, what remains is the question the documentary has been circling from the start. How long could it last, and what must it be willing to become to last that long? The next chapter moves toward resolution, and it does so without comfort. It asks for a realistic survival horizon, and the few design choices that most change the odds when deep space refuses to be empty. The question that opened this film returns with a sharper edge, as if the void itself is asking it again. If the universe offers no shortcuts, how long can a sealed human world endure? By now, the answer is not a single number, because the ship is not a single system. It is a stack of interlocking clocks, each ticking at a different rate, and survival equals the shortest one. Ecology has its own clock, measured in drift, contamination, and lost closure. Society has its clock, measured in legitimacy, conflict, and the willingness to obey constraints. Genetics has its clock, measured in effective population size, mutation load, and the integrity of records. Hardware has its clock, measured in fatigue, corrosion, radiation damage, and maintenance capacity. The survival horizon is the minimum of these clocks, not the average, and that difference is brutal. A ship can have perfect radiators and still die from a governance collapse. A ship can have stable institutions and still die from ecological runaway. A ship can have a thriving biosphere and still die from an unfixable manufacturing gap. Visually, imagine 4 dials in a dark control room, their needles moving at different speeds. The crew can celebrate 3 needles holding steady, yet the 4th can be sliding toward red. Start with ecology, because it is the most alive and the least forgiving. Closed loops are never perfectly closed, and small losses compound into missing atoms. Every loop has seams, valves, gaskets, sampling ports, human hands, and seams are where matter escapes. Even a few grams per day becomes tons over a century, and the math never negotiates. Air and water can be recycled, yet filters saturate and membranes foul. Microbes adapt to disinfectants, and biofilms turn plumbing into a habitat. A biofilm is not just slime on a pipe, it is a layered ecosystem with gradients of oxygen and chemistry. Inside that thin film, bacteria trade genes, resist cleaning, and quietly change the ship's microbial baseline. Carbon dioxide scrubbing looks simple on a schematic, yet sorbents age and catalysts poison. Trace compounds accumulate to solvents, plasticizers, aldehydes, and they can drift upward until symptoms appear. Water loops have their own slow dramas, because dissolved salts and organics behave differently than pure H2O. Distillation, reverse osmosis, and ion exchange can recover most of it, yet each step creates brines and waste streams. Food systems can be efficient, yet they are narrow in diversity and sensitive to disease. A single crop dependency becomes a single point of failure. In a greenhouse bay, the camera could linger on perfect rows of leaves under violet LEDs, beautiful and slightly uncanny. That beauty hides fragility, because uniform plants share uniform vulnerabilities. Plant pathogens evolve quickly in closed environments, especially when the same varieties are grown year after year. Fungi and viruses do not need malice, only opportunity, and monoculture is opportunity made permanent. Pollination becomes a policy question, not a pastoral detail, when insects are scarce or absent. Hand pollination, robotic pollinators, or carefully managed bee colonies each add labour, risk, and another dependency chain. The ecological limit is often not one dramatic crash, but a slow narrowing of margins. Each workaround adds complexity, and complexity becomes its own leak. Engineers call it a mass balance. but residents experience it as a creeping sense of constraint. The menu narrows, the air feels drier, the maintenance schedule grows teeth. Monitoring pushes that horizon back because early detection buys time. Metrology becomes an organ of the ship, and trend literacy becomes civic knowledge. Sensors are not neutral decorations, they are the ship's immune system, watching for subtle inflammation. A few parts per billion of an unexpected compound can be the first whisper of a failing seal. Calibration becomes ritual, because uncalibrated numbers are comforting lies. A century into the voyage, the meaning of a normal must still be anchored to standards that have not drifted. There is a historical echo here, because Earth has run closed-loop experiments before. Biosphere 2 taught how hard closure is, and how quickly CO2, soil microbes, and human psychology can surprise designers. Those lessons do not condemn the idea, but they remove innocence. They suggest that a generation ship must treat ecology as a living research program, not a finished product. Next is social cohesion, because every technical fix requires coordinated behavior. The ship cannot resupply, so it must continuously resupply itself with trust. Trust is not a mood, it is a working material like oxygen or copper. When it thins, every repair takes longer, every warning becomes political, and every emergency becomes a referendum. Chapter 5 framed legitimacy as life support, and that remains the central constraint. Rules that feel unfair become non-compliance, and non-compliance becomes system instability. In a sealed habitat, small acts of defiance can have large physical consequences. A bypassed filter, an unreported leak, a hoarded nutrient stock, each can ripple into system-wide risk. A rigid constitution can preserve predictability, yet it can become wrong in slow motion. A living charter can adapt, yet it can be captured by fear and charisma. The camera might show a council chamber with worn handrails and patched walls, where the same arguments recur in new accents. The setting changes slowly, but the stakes never do. Emergency powers are the recurring stress test, because deep space manufactures emergencies. If exceptions become permanent, then maintenance becomes politics, not engineering. Even the definition of emergency can drift, especially when leaders learn that crisis unlocks obedience. The ship must design triggers that are measurable, because vague triggers invite permanent rule. Mission drift is the long shadow behind every generation. Arrival denialism and returnism are not madness, they are responses to inherited sacrifice. A child born under metal ceilings did not choose the launch, and that fact never stops being true. So the ship must answer a question that no machine can answer. Why keep going? The ship must engineer meaning as carefully as it engineers oxygen. Education, ritual, and conflict resolution are not decorations, they are control loops. Education is also technical continuity, because procedures decay when they are memorized without understanding. A manual can survive on a server, yet its intent can vanish if no one can explain the reasons. Ritual can sound irrational, but it's often a compression algorithm for values. A yearly maintenance festival, a public audit day, a shared remembrance of past failures. These can bind strangers into a crew. The likely first failure in a well-built ship is social or biological, not purely mechanical. Machines can be redundant, yet legitimacy cannot be stockpiled like spare parts. Redundant pumps do not argue with each other, and backup batteries do not form factions. Humans do, and that is why governance must be treated as load-bearing structure. Now genetics, because time turns a population into a math problem. In a closed system, effective population size shrinks under inequality, stratification, and reproductive skew. Effective population size is not headcount, it is the number of people who actually contribute genes to the next generation. If a few lineages dominate, drift accelerates even when the ship feels crowded, inbreeding rises unless actively managed, and drift erases options without asking permission. Radiation adds mutations, and selection quietly tunes humans to ship conditions. Drift is silent because it does not announce itself as a disease. It simply removes variants, and once removed, they are gone unless stored elsewhere. Radiation is a constant tax in deep space, even behind shielding, because high-energy particles can penetrate and fragment DNA. Most damage is repaired, yet the repair is not perfect, and small errors accumulate. Selection can be subtle and unsettling because it may favor traits that fit the ship rather than the destination. What happens if low-gravity development shapes bodies for corridors, not for a planet? The cryobank is the external continent of diversity, and it is also a fragile promise. It depends on power, maintenance ritual, and records that remain legible across language drift. In a cold storage vault, the visuals could tighten to frost on metal, vapour curling from a seal, and warning lights reflected in glass. The bank looks like certainty, but it is a machine that must be believed. Records are as critical as nitrogen and electricity, because a mislabeled sample is a genetic lie. Over centuries, names change, scripts evolve, and databases migrate, so the ship must preserve meaning, not just data. If the bank fails, the population plan collapses into improvisation. If the bank loses trust, governance collapses into coercion, and coercion feeds resistance. Genetic management can extend the horizon, yet it carries political risk. Screening and embryo selection can become a legitimacy crisis if consent is not durable. Consent is not a signature frozen in time, because the governed population changes. The ship must decide whether the unborn can be bound by the decisions of the dead. Then hardware entropy, because physics charges interest forever. Radiation flips bits, impacts pit surfaces, seals harden, and metals fatigue under cycling stress. Fatigue is especially unforgiving, because it punishes repetition rather than magnitude. A small pressure change, repeated millions of times, can grow a crack that no one sees until it matters. Corrosion is chemistry with patience, and closed habitats are not chemically simple. Humidity, trace acids, and dissimilar metals can create slow galvanic battles in hidden joints. Electronics age too, because semiconductor lattices are not eternal. Single event upsets can be corrected, but cumulative damage alters thresholds, and eventually the component becomes unreliable. A ship survives this only by treating replacement as normal. Modularity, standardized parts, and design for disassembly turn entropy into scheduled work. The visuals here are hands and tools, not heroic panoramas, a panel removed, a connector cleaned, a worn bearing measured. The romance is in the discipline, because discipline is what keeps the lights on. Manufacturing is the hinge between centuries and millennia. Without industrial self-sufficiency, the ship becomes a museum of irreplaceable components. A museum can be beautiful, yet it is defined by what cannot be touched. When a critical part becomes too precious to replace, the ship has already started to die. With manufacturing, the ship becomes a flying city-state with an economy. It must mine its own scrap, refine feedstocks, and maintain metrology and quality control. Scrap is not waste in a closed world. It is all waiting for attention. The ship must sort alloys, recover rare elements, and track contaminants that would ruin a melt. Quality control becomes a kind of internal law, because a bad batch of fasteners can kill more surely than a meteor. Standards must be enforced even when deadlines tempt shortcuts. This is why the endurance question becomes institutional, not just technical. The ship must preserve skills, calibration standards, and the culture of reporting near misses. Near-miss reporting sounds mundane, yet it is a survival technology. It turns shame into information, and it prevents small errors from becoming normalized disasters. So what survival window is realistic given these coupled clocks? With robust redundancy, strong monitoring, and real onboard manufacturing, century-scale survival is credible. That credibility is not optimism, it is an engineering claim with conditions attached. It assumes the ship launches with margin, and that margin is protected like a strategic reserve. A few hundred years is plausible if the ship is designed for repair, not peak performance. It requires buffers in water, nutrients, and spares that politics cannot quietly steal. Buffers are tempting targets, because they look like hoarded abundance. Yet in a closed system, buffers are time, and time is what emergencies consume first. Multi-century to millennial survival demands extraordinary closure and stability. It demands governance that survives repeated crises without turning into permanent coercion. It demands leaders who can say no without becoming tyrants, and citizens who can accept constraint without becoming subjects. That balance is rare on Earth, and harder in a corridor world. It demands an education system that prevents skill collapse and procedure drift. It demands a civic compact that protects pluralism while enforcing non-negotiables around life support. Non-negotiables must be explicit because ambiguity invites bargaining. Air, water, radiation shielding, and structural integrity cannot be voted into weakness without consequence. It also demands ecological diversity over optimization, because optimized systems are brittle. A resilient biosphere includes redundant crops, redundant microbes, and redundant pathways for nutrients. A diverse system looks messy in a diagram, yet it is stable in practice. When one pathway fails, another can carry the load, and the ship gains time to respond. Diversity looks inefficient at launch, yet it buys options later. Options are the only currency that grows in value with time. The design principles that push the horizon back are consistent across domains. Prefer modularity over elegance, repairability over novelty, and transparency over comforting secrecy. Elegance can be a trap, because it often means tight coupling and hidden assumptions. In a long voyage, hidden assumptions become inherited vulnerabilities. Prefer multiple methods that fail differently, so one flawed assumption cannot synchronize every backup. Prefer systems that degrade with warning and teach everyone what warnings mean. Warnings must be interpretable by ordinary citizens, not only specialists, because specialists can be absent or wrong. The ship needs a shared language of risk, and it needs it early. Treat governance as an engineered system with audits, separation of powers, and measurable triggers. Treat culture as infrastructure, because attention and trust are scarce resources. Audits are not insults, they are maintenance for institutions. A transparent audit can prevent rumours from becoming corrosive, and it can keep competence from becoming a closed guild. These principles do not guarantee success, yet they change the odds. They turn collapse from a sudden cliff into a negotiable slope. A negotiable slope still ends somewhere, and that is the point. It gives the ship room to choose. Choice is the only antidote to panic. Then comes arrival, the second crucible that can erase a successful voyage. The destination is not an ending, it is a phase change in identity. For generations, the ship has been the map and the territory at once. At arrival, the territory expands, and that expansion can feel like loss. After centuries of enclosed microbes and managed exposure, a new biosphere is a shock. The arrival bottleneck is medical, ecological, and psychological at once. Immune systems trained on ship flora may overreact or underreact to alien biochemistry, even if it is only subtly different. Quarantine becomes both protection and provocation. Even if the ship reaches the star, it must brake, maneuver, and allocate power under stress. The ship can survive cruise and fail the transition into settlement. Braking is not a single burn, it is a long campaign of energy management. Heat must be rejected, propellant must be rationed, and every maneuver is a chance for cascading failure. Some will want to stay aboard because the ship is the only world they trust. Some will demand landfall as liberation, even if the planet is hostile. Both impulses are rational, and that is why the conflict is so dangerous. When rational fears collide, compromise can feel like betrayal. Governance must absorb that conflict without turning it into sabotage. The settlement plan must be flexible enough to accommodate both caution and urgency. Flexibility can mean staged landings, orbital habitats, or a long period of dual residence. The exact plan matters less than the legitimacy of the process that chooses it. This is where the film's themes converge into a cosmological reflection. Interstellar distance forces humanity to treat time as a resource, not a background. On Earth, time is often treated as a generous river. In interstellar flight, time is inventory, and every decision spends it. A generation ship is an artificial Earth in the cosmic dark. It reveals that survival is not a miracle, it is a continuous practice. The ship mirrors Earth in one unsettling way. It is finite, fragile, and sustained by constant vigilance that can never be fully automated. Automation can reduce workload, yet it cannot replace responsibility. When the unexpected happens, someone must still decide what to sacrifice, and why. It also mirrors Earth in one hopeful way. If designed as a civilization, not a vehicle, it can carry continuity farther than any individual life. Continuity is not sameness, because cultures evolve, languages shift, and values reweight. The question is whether evolution stays compatible with the mission, and whether compatibility can be chosen. So the central question can finally be answered without pretending it is simple. A generation ship could survive for centuries if engineered as a closed, repairable biosphere with stable institutions. The ultimate limit is the coupled fragility of ecology, society, and entropy. That limit can be extended, buffered, and managed, yet it cannot be eliminated. The final unknown is not the physics of the void, which can be measured and budgeted. The deeper mystery is whether a civilization can choose to remain itself across generations. What does it mean to remain itself when no one remembers Earth firsthand and the sky is always a ceiling? What happens when the promised world is real, but the ship has become home? It must do that without rescue, without resupply, and without anyone alive remembering the promise firsthand. In the end, the ship is not only crossing space, it is crossing time. Across this journey, the distance to even the nearest star stopped being romance and became arithmetic. A light year measured in oxygen, calories, spare parts, and patience. We watched engineering turn into ecology, ecology turn into genetics, and genetics turn into politics, until the ship looked less like a vehicle and more like a small sealed planet. In deep space, nothing is ever truly closed, so survival becomes a slow accounting of leaks, radiation damage, microbial evolution, material fatigue, and the stories a society tells itself to keep repairing. The machine side was never just engines and hulls, it was gravity that must be manufactured, heat that must be rejected, and shielding that must be paid for in mass. Rotation promises health over centuries, yet it demands structures that can endure creep and fatigue, bearings that cannot quietly fail, and a culture that treats inspection like prayer. Radiation was the patient predator in every chapter, rewriting DNA one hit at a time, flipping bits in memory, and forcing layouts where water is both drink and armour. Even the empty interstellar medium became weather, turning dust into bullets at velocity, and making the forward hull a ledger of impacts that must be sensed, patched, and understood. Then the documentary's centre of gravity shifted inward, to the biosphere that must never stop cycling. Air is chemistry with almost no buffer, water is a battle against fouling and trace toxins, and food is an energy budget disguised as agriculture, with pests and pathogens evolving on the same timetable as the crew. Nitrogen, that invisible constraint, ties farms to either fragile microbial niches or industrial fixation, and either way it becomes a policy choice as much as a technical one. Over centuries, the hardest failures are rarely dramatic, they're trend lines, a few grams lost per day, a calibration drifting, a biofilm learning the system better than its operators. The population itself became another closed loop, governed by effective population size rather than headcount, and by drift and inbreeding rather than optimism. Cryobanks looked like an external continent of diversity, but also like a fragile treaty with the future, dependent on power, maintenance rituals, and records that must remain legible through language drift and regime change. Reproductive rules, pairing guidance, screening, and gene therapy can push the survival horizon outward. Yet each tool creates new questions about consent, stigma, and who gets to define healthy when the habitat cannot afford failure. And beyond the ship's walls, the arrival bottleneck waited like a second planet-sized problem, because a crew adapted to their own microbiome may meet an alien biosphere with immune naivete, turning first contact into a medical crisis. Finally, we reached the quiet conclusion that governance is not a layer on top of life support, it is life support. A rigid founding constitution can prevent panic majorities from voting away oxygen, yet it can also fossilize into brittle scripture when conditions change. A living charter can adapt to new realities, yet it invites capture by those who control information, emergency powers, or the narrative of sacrifice. Mission drift, arrival denialism, returnism, competing myths that sacralize the ship, emerges not as a side plot but as a structural threat, because a closed world cannot tolerate sabotage and cannot exile its dissent. And so, the survival horizon we traced was never one clock but four, ticking together. Hardware entropy, ecological drift, genetic narrowing, and legitimacy. You can overbuild one domain and still die to another, because every subsystem borrows from the same finite budgets of mass, energy, attention, and trust. The ship endures only if it becomes a self-repairing civilization, with apprenticeship pipelines, audit trails, calibration culture, and the humility to treat normal operation as ongoing research. In the end, the Generation ship is not defeated by the drama of a single catastrophe. It is tested by the accumulation of small debts that must be paid forever. It must keep its radiators breathing, its hull healing, its farms diverse, its microbes watched, its children educated, and its laws believable. Even the cryobank, our most tempting cheat code against genetics, must survive politics, semantics, and suspicion. or it becomes a broken promise that destabilizes the very plan it was meant to save. And when the long cruise finally ends, the ship must still do the hardest thing of all, braking, transitioning, and meeting a new world without letting the old one collapse in celebration or fear. So what breaks first? The machines, the biology, or the people? And how long could a generation ship really survive in deep space? The most honest answer is that it survives until one of its 4 clocks runs out. And the earliest clock is often legitimacy, because politics is the first leak that can't be patched with spare parts. With redundancy, manufacturing, and disciplined monitoring, the hardware and ecology can be stretched for centuries, maybe longer, but only if a society can keep choosing constraint, maintenance, and shared reality, generation after generation. A generation ship's lifespan is not decided by a single technological miracle, but by the long, quiet negotiation between physics, biology, and human nature. And that negotiation never ends. It only changes its terms. If we ever cross the stars, the triumph will not be speed. It will be learning to keep a world alive when it is all you have. If this voyage unsettled you, let it, because the first generation ship we must learn to sustain is the one we already live on.